has derived strength from almost all the topics in optics. And I'd like to mention speckles, singular optics, computer holography, digital holography, typography, diffractive imaging, single pixel imaging, compressive sensing, ghost imaging, biometrics, optimization algorithms, chaos, elliptic functions, and nanophotonics, etc. So almost anything that you can think about, including, of course, quantum optics. Cryptanalysis means that you attack the system using various techniques, and for certain types of attacks, in fact, phase retrieval algorithms play a very important role. And the interesting thing is that the quest for improved retrieval algorithm, phase retrieval algorithms, still continues. And Dr. Kehar Singh has done some very outstanding work in this direction. And of course, on singular optics, as you know, Mr. Senthil Kumaran has written a book and done some very outstanding work. Okay. My current interest happens to be in using various tools of artificial engineering, particularly deep learning, through convolutional neural networks, because these can successfully attack almost any systems. But these results are still in infancy. We have no publications on that, so I'm not really presenting anything today on this particular topic. Those who want to have a deeper knowledge of optical cryptography should read this book by Naveen Nishal, listed at the bottom, Optical Crypto Systems, published by IOP in 2020. It was at the initiative of Professor Sirohi, in fact, that this book came out. So this is the flow diagram of a nonlinear optical system, which was described by these three authors from China in 2020 in Optics and Laser Engineering. A shows the encryption part and B shows the decryption part. So we start with an original image, bond it with the random phase code, random phase mask EK1, add a nonlinear term and x1, y1, t. It's a time varying term generated through random generation of number. Do a Fourier transformation, and then multiply by another key EK2, do an inverse Fourier transformation, and you should be able to get the encrypted image. It's very interesting in this particular work that the nonlinear term does not play a role in decryption. And the beauty therefore is that it need not be sent to the person who is accessing the system, and therefore there is no question of key management, or you can say that key management is very easy. Key management is always an issue in optical cryptography. So in decryption, you just have encrypted image, Fourier transformed, and multiplied by the complex conjugate of the decryption key, encryption key, which now is the decryption key, and an inverse Fourier transform gives you the decrypted image. Now on top is shown the usual 4F system, but I have doubt whether in this particular paper they could have implemented the optical system. In fact, they have not claimed that they have implemented the part experimentally, and my doubt stems from the fact that this nonlinear term is an additive term, and to do addition to an image, already existing original image, multiplied by the mask by optical means is a very difficult task, because we know that by optics you can multiply things easily, but addition and subtraction are possible but very lengthy. So anyway, I'm taking this as a digital processing technique because that's what they have presented also, although they claim that they can implement it by optical means, but they have not implemented. So down below on the left, the size of this slightly gray part, not gray, really yellowish part, very light yellow, is 400 by 400 pixels, and it's a multiplication of the original image I by the random mask R. And all around as a border, you see the nonlinear part N as a function of x1, y1, t. So the total becomes 600 and 600 pixels. So that means all around it's padded with zero padded with pixels. So this is the additive term I was talking about. I have already said that nonlinear term does not play any part in decryption. It does not influence the decrypted image. Now, the authors of that paper claim that it's resistant to conventional known plain text attack, chosen plain text attack, and cipher text only attack. And we have verified this. Their claim is bona fide. It's really immune to these systems. So they used the technique of phase retrieval and simulated annealing in case of one of the attacks. And they forgot something because they applied the conventional technique of these attacks, these KPA, CPA, and the...
Sir, 2 minutes more.
Oh my God. Cipher text only attacks. So the input image, random mask, and nonlinear terms are shown here. RPM2 and encrypted image is also shown here. And if everything is known, that means the keys are known to the person, you have to be able to retrieve it as A and B. B has been obtained by subtracting the pixels from the decryption. Now, we modified these attacks, the conventional attacks, and then we were able to attack the system and show that the system is not really immune to these. I will avoid these mathematics and show you only the results. So for modified CPA, these are the results. You have the original image, recorded image from MCPA, and the final retrieved image. Then the modified known plain text attack, the flow chart is shown here. I'd like to spend a minute here. IP is the original image. It's bonded with the random phase for initialization. Then Fourier transformed to give p to the power I5. Then you generate a function, which is the encrypted image, f. Here, it's the Fourier transform of the encrypted image. So you get a function g is equal to f by p to the power I5. Then you create fg star, inverse Fourier transform it to get I1 e to the power I psi. Then do a correlation coefficient analysis between the original image and I1. If it is very good, let's say above a certain threshold t, then yes, the image will be good. Otherwise, you go through this loop again. And we applied certain Fourier constraints and spatial constraint on these, which is not necessary really in the conventional attacks. So using this iterative procedure, after 5,000 iterations, you get quite good images. The correlation coefficients in C and D are 0.848 and 0.808 for these two images. Now, what is the road ahead? The road ahead, as I mentioned earlier, is to use the tools of artificial intelligence, like deep learning through CNN. So we are trying that, although these need very high computational loads. Applications in big data, like authentication, optimization, more powerful attack algorithms. Miniaturization of systems, which I have been advocating in various conferences for the last 5 years or so, using micro and nano photonics. And now it's really possible because there are a large number of papers now where they have reported generation of holograms of meta surfaces, which are two-dimensional surfaces, and almost all the conventional optical components like mirrors, prisms, beam deflectors, and lenses, etc., can be generated using these holograms. And another possibility is that you marry concepts from quantum optics, quantum physics, with the conventional optocryptographic systems to come out with hybrid systems, because purely quantum encryption, pure quantum encryption demands huge investments. Now, what will the shape that optics 80 will take? There are many variables. I don't know. Your guess is as good or as bad as mine. So thanks for being patient listeners. And with that, I'll sign off. Thank you very much.
Thank you very much, sir, for this very nice description of what you are doing today. So I'm sure not only optics at 80, optics at 90 and 100 will go on, and we look forward to many more contributions from you. If there is any question, although we don't have much time, but just one question we can take.
Anuragji, can I ask a question?
I knew, sir. I was just going to say, Professor Sururi.
I know that.
I knew that.
Photonics.
I knew it was coming.
Hello, do you hear me?
Yes.
Kehar Singh, do you hear me?
Yeah.
In electronics, we have 32-bit encryption, 64-bit encryption, and so on.
Yes.
Is there something like that you can assign to your optical encryption? And do you really have some applications of this, or do you foresee some applications of this?
Applications of optical techniques, you mean?
That is all.
Yes, I think that's what he means. Yeah.
Oh yes, in document security for almost all applications, like in defense, like in biomedical engineering, keeping the data of patients secret, in communication, in optical communication, for example. Of course, I'm talking of the images, but it has been applied to optical communications. Authentication purposes, e-commerce. So you prodded Professor Naveen Nishchal to write this book. It's published. Why not read it?
I requested him to do because you did not do it.
Yeah, why not read it?
So that is why I
requested
him to do.
Yeah. Thank you for
this
discussion. Yeah. Okay.
Can you see my screen?
Yes. So next talk is by Professor Ghatak, and if anybody who is in this audience does not know Professor Ghatak, you get to start at t equal to 0 again. Okay, so let's hear Professor Ghatak.
I have put it in the slide mode. Can you see that?
नहीं, आप स्लाइड को वो कर लीजिए प्रेजेंटेशन मोड.
हाँ, कर लिया.
नहीं हुआ अभी वो.
हाँ, अभी चलो इसी तरह से करते हैं.
कभी-कभी नहीं होता है. You can proceed, sir.
अच्छा. So you can see the slides?
Right.
अच्छा. So I'm going to. I would first like to congratulate the organizers for having this workshop celebrating 80th birthday of Professor Kehar Singh, and I think other than Professor Sirohi, I know him for the longest period of time, and I met him first on May 1966, and we have spent many happy times together, and as you can see, I am laughing with my full thing, and he smiles. He does not become too excited about small things. So it has been really a very enjoyable association. So I'm going to talk to you about two-slit interference, which is very simple. But I thought to entertain all of you, I will talk about the most beautiful experiment in science. That's what Robert Crease has described it as. And here is a gun emitting tiny bullets, and this is adapted from the Feynman lectures. You have two slits. The bullets go either through slit number 1, slit number 2. Switch off your microphone.
ये lecture है, ये आपके बड़ा important है आपके लिए, देखो इसलिए.
Please switch off your microphones. So the bullets will either go through slit number 1 or through slit number 2, and so when both slits are open, you will get a P12, which is P1 plus P2. Now,
सर मैं सबको म्यूट ऑल करता हूँ, फिर आप अपने को अनम्यूट कर लीजिएगा. सर अपने को अनम्यूट कर लीजिएगा आप.
Sir is not audible.
साउंड नहीं आ रहा सर.
सर अपने को अनम्यूट कीजिएगा.
Professor Ghatak is mute.
can you hear me now?
Yes. Okay.
Now it
Yes,
is.
sir.
Oh, sorry.
Yes, sir.
So then let me start from beginning.
Yes, sir.
So this is the two slit interference. Can you hear now? Can you see the
Yeah.
slide now?
Yeah.
Yes, sir.
Reach the
Yes, sir.
third
This
slide.
is my photograph with Professor Kehar Singh. And I had known him since 1966, and it has been a very enjoyable association. So I'm going to talk to you about the two slit experiment, which is one of the most simple and at the same time very elegant experiment in optics. So if you did with bullets, like coming out from a gun, then you don't see any interference. The bullets either go through slit number 1 or slit number 2, and when both slits are open, you get the intensity distribution, which is P1 plus P2. Now, as you all know, Thomas Young carried out the experiment in 1801, and I'm sorry. And he created the interference pattern, and he could measure the wavelength of light, and he could say that light plus light could produce darkness. And I thought I will tell you that there is a book by Andrew Robinson about Thomas Young as the person who, the last man who knew everything. Then wave theory of light was established, as you all know, and in 1905 Einstein came with a phenomenal paper in which he quantized the light. He introduced the light quantum, whose energy was h nu and momentum was h nu by c. So the wave particle duality was introduced by Einstein in his year of miracles. Now, as we all know, J.J. Thomson introduced the electrons, discovered the electrons. We now know the mass of the electron and charge of the electron to 10 decimal places. And so we imagine that as a tiny, small, tiny particle. Then Louis de Broglie in 1924 said that since the momentum of the photon as put forward by Einstein is h by lambda, electrons must also have a momentum, have a wavelength associated with it, which is h by p. So he introduced wave particle duality for electrons in 1924, which was experimentally verified by Davison and German and G.P. Thomson. And you can see the diffraction patterns produced by aluminum foil, by X-rays, and by electrons. So the wave nature of the electron was established, and then came the wave particle duality. And so therefore the question is the electron or a proton a wave or a particle? This is a question which has bothered many people. Feynman has written that they are neither waves nor particles. So what are they? No one really knows what are they. They are described by the wave function psi, which is the solution of the Schrodinger equation. So an electron is described, a free electron is described by the wave function psi, which is the solution of the Schrodinger equation. And Feynman writes that where did we get that equation from? Nowhere. It is not possible to derive it from anything you know. So the Schrodinger equation cannot be derived. Where did it come from? It came out of the mind of Schrodinger. I'm quoting Feynman because if I said that, probably you will not believe it. So let me talk about the one-dimensional Schrodinger equation. As you all know, if you use the method of separation of variables, then you will get this as the solution, where px can take any value from minus infinity to plus infinity. I'm just restricting to one dimension. So the most general solution of the Schrodinger equation will be a wave packet, which is an integral over different values of px, and Max Born, for which he got the Nobel Prize, gave the physical interpretation that mod psi squared dx is the probability of finding the electron between x and x plus dx, and apx squared dpx is the probability of finding the x component of the momentum between px and px plus dpx. So the recipe is that if I know the wave function at t equal to 0, so then you put t equal to 0 and this becomes this. So you can use the inverse Fourier transform to calculate a of px, and then you substitute it here to study the evolution of the wave packet. So let me first discuss the single slit diffraction pattern. So for that, the particle, the electron passes through the slit. So the wave function at t equal to 0, the x part, not x component, x part of the wave function is given by this. And if I substitute that in the expression for a of px and you carry out the integration, then I will obtain sine beta by beta. And if you square that and multiply by dpx, you will get the probability distribution of the momentum. Now this is the most important slide. So therefore Schrodinger equation tells us that if you confine the electron within a distance of b, the slit system imparts a momentum, and the probability of the momentum lying between px and px plus dpx is given by this expression. So the particle was localized within a distance b, the spread in the momentum is h cross x, so that product is h cross. So contained in the solution of the Schrodinger equation is the uncertainty principle. So everything is contained in the solution of the Schrodinger equation. And as you all know, that the classical intensity distribution associated with the single slit diffraction pattern is given by this. So the probability distribution is the same as the intensity distribution, and so therefore where will the electron hit the screen? No one can predict. One can only predict a probability distribution. So classical physics is deterministic in nature, but quantum physics is probabilistic in nature, and so therefore that is the most important revolution that has taken place with the advent of quantum theory. And as you all know, Einstein never believed in it. So I will now discuss the double slit experiment, in which I have the electron now confined between the two slits. So the initial part at time t equal to 0, I assume a wave function which is 1 over square root of b in one of the slits and one of. So the electron is described by a wave function which is finite at one slit and the other slit. So in a way, electron passes through both the slits at once. So I assume a wave function like this, calculate a of px, and I square it and multiply by dpx, and I get the same intensity pattern as I would obtain in solving the wave equation. So this is the probability distribution as predicted by quantum mechanics, and this is the intensity distribution as predicted by wave theory, and you can see both of them are identical. And so therefore, if you carry out the double slit experiment with the electron, then you expect P1 plus P2, but you get an interference pattern. And so therefore the electron passes through both the holes at once. And there is a very beautiful experiment which was done by Tonamura in 1989, in which he showed single electron interference experiments. He used single electrons to pass through both two slits, and eventually when you have 70 or 100 electrons, there are 100 different spots, so that you measure the electron, either one electron or no electron. But if you did with millions of electrons, then slowly the probability distribution evolved. This is considered as the most beautiful experiment in physics. So therefore, as Richard Feynman says, electrons do not behave just like particles, or they did not behave just like waves. Electrons in orbit are not somewhat like a cloud or fog of some sort surrounding the nucleus. It behaves like nothing that you have seen before. Well, there is one simplification at least. Electrons behave exactly the same way as photons. So therefore, to summarize, the two-slit experiment with electrons, which contains the entire quantum mechanical concepts associated with it, the electrons coming out of the filament passes through both the holes simultaneously. It is not the splitting of the electron into half and half. If there were 3 slits, it will pass through the 3 slits simultaneously. And it predicts a probability distribution. Now, the question arises, if the electron has a definite mass and a definite charge, how does it pass through both the electrons? That no one understands. That no one understands. And therefore, Feynman's, at the end of his messenger lecture, I will ask all the students to listen to this lecture. He also said that the interference experiment has been designed to contain all of the mystery of quantum mechanics, to put you up against the paradoxes and mysteries and peculiarities of nature. And then he finally says, I think I can safely say that no one understands quantum mechanics. But and that is true also for light, because Albert Einstein in 1917, when he put forward the stimulated emission of radiation, he said that for the rest of my life I will reflect on what light is. And then in 1951, 4 years before his death, he said that all the 50 years of conscious brooding have brought me no close to the answer to the question, what are light quanta? Of course, today every rascal thinks that he knows the answer, but he is deluding himself. So I am just an old storyteller. I do not know what the truth may be. I tell you the story as it was told to me. Thank you very much for giving me the opportunity of presenting this 13-minute talk. Thank you, Anurag.
Thank you very much, sir. Thank you very much for keeping time. That's really great. So if there are any questions here, we can take.
Professor Ghatak, I'd like to ask one thing, sir, if you give me the permission.
Yes.
Yeah, please go ahead.
Short question.
So you can unshare the screen.
Yeah. So you've talked about 1801, 1906, and you've taken us from all the way, the 200-300 years of history. So what is your prediction, like, let's say 100 years from now, where will this theory lead to?
Okay. My answer, yes. Have you finished your question?
Yes, sir. Yes, sir.
So I do not know. But you see, the main thing that I wanted to say in the form of quotations is that no one really understands why and how quantum mechanics works. But it works. It gives us a tool which allows us to predict quantities which are verified to 10 decimal places of accuracy. So therefore it works. And so therefore one really does not know what an electron or a proton. We have recently observed, not we, I mean Zillinger has observed the interference pattern with fullerene molecules, which is a big size, like a mini soccer ball. So is that a particle or a wave? It is neither. The main thing is, it is not that it sometimes behaves like a particle and sometimes behaves like a wave. The correct answer, and I quote Feynman so that you can trust me, that it is neither a particle nor a wave. So what is it? The answer is I don't know. So in 100 years, will I know? I doubt it. I will not be there, but I doubt it. Because quantum mechanics is an exact science. We are soon going to celebrate 100 years of quantum mechanics, and it is an exact science. I have full faith in it. I've been teaching basic quantum mechanics for the last 40 years, and I now strongly believe in that. So will someone prove quantum theory wrong? I don't know. I don't hope so. I don't think so, because it works so well.
Okay. Thank you, sir. Okay. Before I move to the next talk, Professor Suroi, you can share your desktop. I mean your presentation.
I have not used this Meet earlier, so how do I share?
There is a button arrow.
Yes, I tried, and I went out of his screen.
No, first Professor Ghatak has to stop presenting.
Yeah.
Now it will work.
Yeah.
No,
In
it is
the
not
meantime,
working.
I welcome C.S. Narayan Murthy, the President of the Optical Society of India.
Yes.
Oh,
This
namaskar.
meeting.
I'm
Of course, there are
apologizing.
6 former presidents sitting here also.
Because I have to make my breakfast because my wife is not here. She's at Bangalore. So I'm locked down for 1 year. So I am sorry
Dinesh,
that.
have I answered your question?
Sharma ji, I'm not able to. I don't get this arrow.
Joby?
Yes, sir. I mean, he is a presenter. There should not be any problem.
Yeah, but I have problem.
So when you press the arrow button, yeah, it's there.
Yes.
No, this is Khatak sir's presentation.
Arrow is not getting pressed now.
सर घटक सर आपने अनशेयर कर दिया?
हाँ अभी कर लिया
Rohit sir should share his screen, then we can tell him.
What?
Can you press the share content button, then press the screen button?
It doesn't. It is not live there. You know this button.
So, can you press Control Shift and E?
Control
Shift and E. Joby sir, good morning. This is Dr. Joshi. I am saying whether you have made him a presenter.
Yes.
No.
So he is a guest in the list.
No, he is a guest, and others are also. Professor Khatak also is a guest.
Okay. It is not getting done. I will go off the meet, and then you please continue, and I will try to log in again. Then you give me a slot.
Yeah. So we'll request Professor Paul to continue, and then you can come back. Next talk will be yours. Yeah.
Yes, if I can.
Okay. Yes, sir.
Otherwise, many happy returns to Kehar Singh.
Thank you.
नहीं सर आप वापस तो आएंगे ही इसमें क्या बात
अब पता नहीं भाई आप आने देंगे या नहीं
You are always welcome, sir. We are.
आपको कौन रोकेगा चलिए हाँ प्रोफेसर पाल
Yeah, Anurag. Yes.
So you can make the presentation. So Joby has to share.
Yeah. Should I share, sir? I have made you a presenter. You will be able to present, I think, Pal, sir.
I just try. Let me try once. Just.
Yeah. Otherwise, I will present.
Here.
Can you see it?
Not yet.
I can see on my screen. Can you don't see it? Is it? Screen share.
Yeah, screen share, and then press the screen or any application.
I think somebody has to give me permission to share. It is not there.
Let me see.
सेलेक्ट करने का ऑप्शन नहीं है
Sirohi sir, can you try now? Maybe there was some confusion. So, can you try now, sir? Sirohi sir? Yeah, now it's fine. It's there. Sirohi sir, it's fine.
You can continue. So your time starts now, sir. Sir, you have to unmute, I think.
Sirohi sir, your sound is not coming. We are able to see your slide.
सुरेश जी आप म्यूट हाँ आप ठीक है अनम्यूट कर लिया आप
Are you able to see our slide?
Yes.
But I am not able to see. Oh, here it is. No.
Yeah, good sir.
Good. Huh?
So screen.
Okay. All right. I'm going to talk about this shareography, a technique for non-destructive testing. And let me see how it goes now. How do I move it here?
Press down.
It doesn't move here also. This is not the one.
Page down, sir. Page down से हो जाएगा.
Sir, you can use any arrow keys.
I can't move it up and down. Okay. Yeah. Okay. So these are the contents, and I'm going to be very fast. Okay.
Yeah.
Now, this is the first paper by Linders and Butters in 1973. And what they did a very simple experiment, illuminated the object with a coherent light and imaged it through a Michelson interferometer. Their idea was to get the derivative of the out-of-plane displacement. And these are the kind of fringes they obtained. Similar kind of experiment they did holographically, and then they showed that they can get the same kind of fringes by superposing two transparencies and sliding them so that a moire pattern which will be similar to that obtained by using this experiment. Now I have tried to define what is spherography. As you can see, it is a combination of speckle pattern interferometry and shear interferometry. Here is the speckle pattern interferometry. You make an image of an object and add a reference barrier so that you have an interference record of the speckled image of the object. In shear interferometry, we have the wave which is sheared by some kind of arrangement. In this particular case, we have taken a Mach-Zehnder interferometer, and by tilting one of the mirrors, we can shift one beam with respect to the other, and therefore this beam is sheared. If I combine both of these, I get to the shear interferometry. There are some important features of this one. You will have this on. And this is the basic theory. What happens? You have an object which is recorded as a first exposure, then it is loaded. Loading can be done mechanical, thermal, pressure, vacuum, and so on, and it deforms. So a point P is imaged as a point P prime, a point Q is imaged as a point Q prime, and the light from P prime, Q prime create the second specklegram, and the first one is P and Q, and P and Q are the points which are due to the shearing. It means on the object there is a single point. Passing through the shearing arrangement, we create 2 points, and the beauty of this one is that we do not require a reference wave. And these are some of the equations which but most important part is that in photography we have a recording which is only additive. In electronic recording, we can have subtractive as well as additive. Subtractive has an advantage in the sense that we can remove the DC speckle part. And what is these fringes represents? If you look at the theory part, you will find that if the geometry is such that I illuminate the object normally and see it normally, then I get the derivative of the out-of-plane displacement. And if I illuminate it symmetrically and view it normally, then I get the derivative of the one of the in-plane component. These are various kinds of shearing arrangement people have used: a Michelson, a Mach-Zehnder, a wedge plate, a biprism, and plane parallel plates, Wollaston prism with polarizer, grating. There's all kinds of things, but we have used mostly the apertures and the wedge plates and dot prisms. Our work actually started long ago in 1980s, and we were the first one to actually start the electronic speckle pattern interferometry at IIT Madras. This is about phase shifting. We like to do phase shifting when we want to draw a quantitative data. And there are 3-step, 4-step, 5-step, or n-step phase shifting algorithms. These are various methods, which are used to stress the object in between two exposures. And if we look at the surface, if we look at the strain tensor, you see this is the strain tensor which comes from the material science. Only these components which are highlighted, these are the ones which we can measure with shearography. So we are not able to measure the whole strain sensor, and therefore the shearography measures only the surface strains. And as you can see here, du over dx, dv over dx, d omega over dx, where the shear is along x direction, and uv, w are the components of the deformation vector. We can get them provided I have 3 directions of illumination or 3 directions of observation. So there are setups people have done where they use the 3 directions of illumination and do the recording in sequence, or can use 4 directions or 3 directions of observation. These were some earlier experiments which we did actually, and we used these apertures in front of the lens, put the wedge plates, and recorded derivative of the displacement along x direction, along y directions. We also recorded the total deformation, and similar kind of work people start doing using phase shifting. This is a paper which appears in 2019, and they create these different shears using a Mach Zehnder kind of interferometer. These are the earlier pictures. The recording is photographic. This is the slope pattern along x direction. This is the curvature fringes you get. This is the slope pattern for a cantilever when it is bent. Now we have a pipe which is pressurized between 2 exposures, and you can see there is a little dent in the fringe pattern. But if the same thing is done with shearography, you see clearly the locations where the defect in the pipe lies. So this is just to show that shearography is more deterministic regarding NDT part. And when we do phase shifting, we record the specklegram, find the wrapped phase, then unwrapped phase, and then use computer and draw these slope pattern. And similarly, when there is a defect, you can see here these fringes due to the bulge, and this is the shearogram, this is process shearogram, and this is finally the presentation where it shows how the bulge looks like, So this is how the NDT part is carried out. I'm now just going to talk about few applications, One is in biomedical applications. This is a phantom which is made out of silicone, and silicone of a different stiffness in the form of balls were inserted. And this is partially pressurized, and one can see the location of these hard tissue, which means it is possible to locate cancerous tissue using shearography. This is one application. The other application is in artwork. This is a painting on a wooden panel, and it is fairly thick, it has several layers, underneath layers, and then finally the paint layer. And when we carry out the xerography, you can see some defective areas, some delocation or delamination. This is the processed xerogram. Here is a painting on canvas. This is the image in white light, and you can clearly see that there are some cracks on this painting which are clearly visible. But when we carry out the xerography, this is the processed xerogram, which shows, the existing, the visual cracks which are seen over here, as well as those cracks which are not visible. So here, the black lines are those which are the visible cracks, and the red lines are those which are seen by xerography. And you can see that it sees more than what is visible, which is behind the paint. And this is an application to aircraft non-destructive testing. This aircraft was out. There was a heavy hailstorm. It got damaged, and these panels are being looked at it. So you can see these xerogram, and this is the process xerogram. There are many other applications, but in the end, I would like to say, from a very modest beginning to visualize derivatives of deformation of plates, beams, and other objects subjected to loading, xerography has evolved an acceptable and powerful technique for non-destructive testing of composite structures used by aerospace and automobile industries. It has found applications in other areas such as artwork, cultural heritage objects, biomedical, and so on. And finally, in 80 years, Kehar Singh, Professor Kehar Singh, in 80 years, you have touched so many lives. Whether you are physically touched them or mentally, I have no idea. Shared so many wisdom and made such a difference to the world. Many happy returns of the day. Happy birthday.
Thank you, sir. Thank you, sir. Thank you very much for keeping time. Yeah.
You may like to ask questions. I made it very short.
Yeah.
People don't like to.
If there are any questions, you can ask.
They are more satisfied with computers. Everything comes out in the form of final data, the deformation maps and so on. But since I belong to an age where we were always looking at fringes, I cannot miss that part. That's why I started with that. Okay, thank you.
Thank you.
And
thank you.
Any questions?
I don't see myself.
There is a hand raised. There are 2 hand raised. Any questions?
Yeah, sir.
Yeah.
Good morning, sorry, sir.
हाँ बोलो.
Yeah, sir. तो सर ये जो xerogram में जो अपना whatever the shear we gave or any deformation is there in the optics or any object, it is going beyond 2 pi. How that interferogram will give that information?
That is what they do. That is what the people do. The wrapped phase, 2 pi times. Anything happens, that is a wrapped phase, and then unwrapping. Algorithms are there, so people use that. It's a standard technique in interferometry. Basically, xerography is an interferometry where you don't need a reference wave. You compare an object with itself or a wave front with itself. Otherwise, it is interferometry, and you follow exactly same kind of protocol like you do for interferometric analysis.
Okay, sir.
Thank you. Any other question? Okay. If none, then thank you very much, sir. You can.
शर्मा जी हम सोने के लिए जा रहा हूँ. Thank you very much.
सुबह सुबह भी आना ना आपको फिर से.
सुबह सुबह आज देखिए पहली बात तो यह है आज तारीख 2 है मेरी यहाँ.
हाँ, I know. तभी तो 3 तारीख में आइएगा ना सुबह.
It is not 3rd July.
I know.
So I want to tell Kehar Singh that from my side, you please take it on 3rd July. Tomorrow I don't know when I will wake up. If I am awake, I will come.
Sure. Okay.
Okay.
डॉक्टर साहब इतनी जल्दी कैसे सो रहे हो?
हैं?
इतनी जल्दी कैसे सो रहे हो आप? मैं तो अभी जगा हुआ हूँ.
बताने में देखिए आप कैसे सोते हैं. हम तो भैया अकेले सोते हैं.
How are you, Ramesh? Good to
Okay,
see
that is Bhagwana. How are you?
How are you? Fine, thank you.
Nice to see you.
Yeah, nice to see
Okay,
you.
now we move on. Professor Roy, you can unshare by
How
the
do
same
I
button.
unshare? I don't see anything here.
No, same button.
अरे
Arrow.
बटन तो नहीं दिखाई दे रहा ना मुझे यहाँ पे.
नहीं वो एरो दिखाई देगा. रेनो वो कंट्रोल ई से हो जाएगा.
इस उम्र में इतना बिजी हो गया हूँ शिव चंद्र की क्या बताऊँ. शौक चल रहा है. मेरे कोलीग का 80th बर्थडे है आज.
आ गया कुछ आ गया. I will
Okay, right. Thank you.
Yeah.
It's fine.
Okay.
Okay, sir.
Okay.
Pal, sir, are you able to share the screen, sir?
Pal. So, Dada, are you going to share or Joby will share?
You have to unmute yourself, Pal, sir.
Can you see?
Yeah, now we can hear you. Yes, sir. Yes, sir.
But can you see the PowerPoint?
No.
Not yet.
Close share tray. So, but share tray is actually one. Share the the arrow is now down. So if I press the arrow again, let me see. Now
you press the button arrow again, and then you press the screen button, and that screen window.
Oh, okay. Screen, yeah. But that is coming your pictures.
Yeah, that's okay. Then you can open your PowerPoint.
Oh, okay. Let me see. Is it coming?
No, okay. You select the PowerPoint which you want to show.
Yeah, I have selected. And
No,
if I
it is not coming.
sometimes, can you see it? No.
No.
No,
Otherwise,
then
you can select the
do one
video.
thing. Let us not waste time.
Okay, I will.
You share.
I will do.
You do that.
Is it okay?
Yes.
Yeah.
Oh, okay.
Okay, Dada, start.
Can I start? Yeah.
Yeah, please.
Yes, sir.
Okay. Good morning, everybody. Right now I work in Hyderabad, but yesterday I came to Bangalore, so I'm speaking from Bangalore now. So, title of my talk is Nonlinear Optics: A Historical Perspective and Snippets of Our Own Research in this Domain. So, first thing first. Next slide. Joby, next. Yeah, so first thing first, I wish Professor Kehar Singh for on this very auspicious occasion of your 80th birthday, a very happy 80th birthday, good health in to you, and many more happy returns of the day. May you continue to disseminate your enormous knowledge and experience in optics and photonics to benefit the students. Professor Kehar Singh happened to be also my neighbor for quite several years in the department and physics, and then also my neighbor at mini campus. Next slide, please. Joby, next. Yeah, so let us consider interaction of light with matter as it is shown in this picture. Next, please. I have put in an animation, so you have to keep pressing actually. Yeah, So at low light intensities, the properties of the materials remain independent of the intensity of illumination, and the superposition principle, as we all know, it holds in this case. For intense light beams, however, the response to the material system to the applied electric field could be nonlinear. Next, please. So here you can see that there's a linear variation of the dielectric polarization induced by an electric field, and for which this well-known equation, linear equation, is shown on the top. And for a nonlinear medium, the polarization versus electric field shows a nonlinear curve, and which can be described by this Taylor series kind of expansion of polarization with respect to the electric field. Next. So two or more light waves can then interact in a nonlinear medium and exchange momentum and energy with each other. The superposition principle, however, is then no longer valid. Next, please. The interaction of light waves with the interaction of light waves then just one second. Yeah, interaction of light waves can lead to generation of optical fields at other frequencies. For example, if you have two waves interacting in the phonic cycle.
I can't hear you, Vishnu.
Sorry. Yeah, okay, I just repeat from here. So around 1926, Vavilov along with Levishин observed 1.5% reduction in absorption, and by shining focusing light by microsecond pulses from a Thomson spark, and at the focal point, the intensity being very large, it drove the medium into a saturation. As you can see at the bottom, when you start with zero electric field, the dipoles are all randomly oriented, and the linear regime, part of those are now oriented along the direction of the electric field, but when it achieves saturation, they are almost all aligned in a particular same direction and no more absorption takes. So the full name of Vavilov was Sergei Ivanovich, who was a distinguished Soviet-era physicist, was an outstanding teacher and enlightener, who had introduced in 1944 the term nonlinear optics to the scientific community. 1960 came the discovery of laser, as you know, and this picture shows, actually this was the kickoff ceremony of the 50th year of laser discovery that I happened to be in Smithsonian Museum in Washington. So Theodore Neumann got this spark of laser light from a rubidium, for a ruby laser in 1960. Now, with the since this laser came in 1960 and people realized its importance, so they immediately, OSI, Optical Society of America, next slide please. Optical Society of America brought a special session dedicated to lasers in March 1961 spring meeting in Pittsburgh, in which one Professor Peter Franken from University of Michigan was an attendant. Next slide, please. So in a much later interview with American Institute of Physics, Peter said that he got bored while attending the meeting. Quote, I kept hearing lasers and fantastic eye surgery, communication, eye surgery, communication, eye surgery, communication, where all anyone could think about, and my mind become wandering. Next, please. So he started doodling some numbers and soon realized that intensity of a 5 kilo pulse laser focused to 10 micrometer could electric field of few megawatts per second.
में उनका 80th birthday है उनका 80th birthday है
so 3 to 4, which is 3 to 4 orders of magnitude below the electric field that holds atoms together, please. But which is strong enough to significantly affect or ionize atoms. He stumbled on the idea that this is strong enough to realize detectable second harmony. I quote Peter, I realized, my God, you have got a second harmony in his recollection, which means if you shine red light to a nonlinear optical medium, you get blue light at twice that frequency. This experiment on a lithium, repeated by some Swedish scientists on lithium niobate using it as a nonlinear medium, red light on the right gets converted like magic into the blue light covers on my one of my notes. Next slide. Next, please. So hurrying back to Michigan University, he set up experiments to validate his idea in a quartz crystal and communicated his results in July 61 to PRL, which got published on August 15, 1961 issue, as you can see here. So pump light comes in, gets into a quartz crystal by a dispersive medium like a prism. It disperses the two wavelengths in two different directions, and that's how he established that indeed you can get a second half. That these are the pictures of the four authors of this paper. Incidentally, Hill, next slide, please. Incidentally, Hill, the last picture, next slide, please. Incidentally, Hill was a sophomore from Franken's laboratory, you'll be surprised, physics class, who apparently had experience of carrying out some impressive electromagnetic compression experiments in his parents' garage, made things work according to Franken. At some later date, when Hill became a big man in the Air Force Research Center, he said, quote, "It's absolutely amazing what it has led to and what it is leading to," said Hill, "and it is helping us understand the nature of nature." Next, please. So this was the physical review paper. You see a blob of light on the right-hand side, which is a localization of the red splotch. That's a, blurry image. And then on the left-hand side, there is nothing, only an arrow. That is because when the lithographer actually got this printed version, he accidentally removed that slight intensity small spot. So the physical review editors suggested that let us put an arrow over at that particular location where it was supposed to. Next, please. So one professor, the previous one, please go back to the previous. So one professor Merlin from the University of Michigan again, he said at a much later date in a review that the whole paper was about the dot, and the dot wasn't there. Next, please. So this is how modern nonlinear optics was born, and connected with that, an important concept is the discovery of phase matching. So after that, the publishing of that paper in PRL, a lot of people in Bell Lab and so on, they started working on generating second harmonic, but surprisingly observed that a certain angle, if you shine on a crystal like KDP, you get much stronger second harmonic. This observation led to propound the concept of phase matching for maximizing the effect. Next, please. So phase matching occurs when pump beam is aligned at an angle for which the right angle at a particularly right angle, which refractive index of the birefringent crystals at the pump and generated second wavelengths are identical for which. Next, please. So crystal birefringence serve to compensate the chromatic dispersion between the fundamental and the harmonic. Next, please. So what is the takeaway? Light can alter its frequency as it passes through a nonlinear optical material. Bell Labs Geodamine and Ford Motor Research Terunome independently published their discoveries on phase matching on the January 1st 62 issue of PRL. It is motivated by this, stimulated by this preprint of Franken's paper. Bloomberg and the Nobel laureate working at Harvard University at that point of time directed his entire research group to work on the theory of nonlinear optics. And the result was a 22-page paper submitted in 1862 and published in September 62 issue of Physical Review. Next, please. So that Physical Review paper contained a wealth of knowledge. They also generalized the problem beyond harmonic generation to four-wave interactions. So researchers from other groups, particularly from Russia, they then also observed a large number of nonlinear phenomena like SRS, SBS, self-focusing, etc., and solitons by Hasegawa's group from Japan in mid-1970s. One of the very interesting nonlinear optical phenomena has been the supercontinuum generation of light. Next, please. So what is a supercontinuum generation? Is that if you shine an ultra short, high-intensity pulse on a suitable nonlinear medium, because of the combination of all these which are listed here, the nonlinear phenomena, this undergoes extreme broadening, almost several hundred terahertz.
2 minutes more.
Sorry?
2 minutes more.
Yeah. So on the right hand side, there is a picture example of that. On the bottom, that is a picture that I'm sharing from our Robert Alfano, who was the first to observe supercontinuum in a liquid nonlinear medium. Next, please. So this was supercontinuum light generated from a microstructure optical fiber, first reported from Bell Lab in ECOC 98. And this supercontinuum phenomena, also a picture taken by when Knox, also finds a place on my cover of my. Next, please. So we did some little bit of work. Just I will give you a little bit of snapshots in that direction. We proposed that we can observe supercontinuum in Bragg fiber in this particular paper with Shania and Sonali Dasgupta was the PhD student. Then we published in JLT on theoretical paper. Next, please. Then based on that, we designed a Bragg fiber, which was fabricated by some of my friends from Russian Academy of Science. And eventually, next please, eventually it was characterized in my school time friend Ajay Kar's lab in Heriot-Watt. And you can see here at the bottom, the black one is the pump, and at around 1050, and then you get supercontinuum light from a 3 centimeter long of that Bragg fiber, which was designed from our design, which was designed by us, and broadening of the light in the form of supercontinuum. Next, please. Just one more result I will show. So this is the optical coherence tomography, is one of the most useful, device which has medical community taken advantage of supercontinuum light, essentially a Michelson interferometer explained in this diagram. Next, please. Because of the broadband supercontinuum light, it can be used in dense rectangular division multiplexing also. So there is an experiment reported from Technical University at Karlsruhe, Anurag's former colleagues there, 26 terabyte of transmission using 325 wavelengths on supercontinuum light, each at 80 gigabit per second. Next, please. Nonlinear OptiScan also is a very hot topic, can generate a comb of evenly spaced frequency that can be used as a kind of optical ruler for measuring time. Next. So we exploited 4-way mixing in a project that was funded by the US government Navy Department, and some PhD work resulted from that. So we made use of microstructure optical fiber, in which the basic material is chalcogenide like As2S3, and surrounded by forming a photonic crystal in the form of air holes. So as a result, next please. In a 4-way mixing, essentially you generate a pump. If it is a degenerate 4-way mixing, you inject a pump wave and you get an idler and a signal wavelength at 2 different frequencies. One below the pump wavelength, other above. The signal is above the pump wavelength. That's what we call as a signal wave. Next, please. Next, please. So we had just one paper I'm showing here to give you a snapshot. We did a large number of papers in that particular direction. So we generated, we showed in theoretically that you can generate by wavelength translation, pumping on a suitably designed chalcogenide microstructure optical fiber at a wavelength of thulium dot fiber laser. You pump around 2 micrometer and you get an output, narrowband output at 4.36 micrometer with an efficiency over more than 24%. Next, please. So the bandwidth next, yeah. So you can see that the wavelength generated, our design fiber has a zero dispersion at the coinciding with the very near the thulium dot pump laser, because at that point, if you pump, you get a very strong nonlinear effect. On the right hand side is the generated 4.36 micrometer pulse that you can see as the media wavelength and this bandwidth of about 16 nanometers. Next, please. I'm almost ending. So we had a similar papers, either broadband or narrowband at different wavelengths. 6 micrometer is of tremendous use in biomedical applications. So next, please. So I'll just signing off here. Next is the acknowledgement. I would like to, I don't repeat the names, but you can see on the screen large number of my former students, colleagues at IIT and collaborators from outside India. And our work in this direction was funded, next please, funded by Office of the Naval Research Global, USA, and UQID through British Council Division of British High Council. Thank you very much. Next slide. Thank you very much. Okay, Anurag, I'm reasonably on time, I think. Yeah.
Okay. Yeah.
Thank you.
Okay. Any question? We can have one quick question.
This is Virendra Mahajan. I just want to comment.
Yeah.
It was second harmonic generation by Peter Franken that brought him from University of Michigan to the Optical Sciences Center as the director. He was the second director of the Optical Sciences Center. He passed away in 1999.
Yeah.
I was a young student in those years, early 70s. Thank you.
Professor Mahajan, good morning from here. I hope all is well. Vishnu here.
Yes, thank you very much. Thank you. Nice to hear your voice.
Thank you.
Okay.
Okay, Honorable.
Any question? If there are none, then we move to the next talk. Professor Tyagarajan.
Yeah, Joby, thank you for operating the slides.
Anurag, I'm here.
Thank you.
Yeah, please share your slides. So this is Professor Tyagarajan, of course, is also very well known, outstanding teacher and all. Yeah, let's hear him.
Can you see my screen?
Yeah, sure. Yes.
Okay. I congratulate Anurag, Joby, and others for having organized this intense one-day workshop. My talk is titled "One Photon In and Two Photons Out." And I would like to begin by wishing Professor Kehar Singh a very happy birthday. I wish him a long life full of excellent health and happiness. And may you contribute to enthuse and inspire more generations of optics and photonics professionals. Congratulations, Professor Kehar Singh. Okay, so the polarization, electrical polarization in the medium depends on the electric field of the propagating light wave. And for strong light waves, essentially the nonlinear terms become important. And you can see the numbers typically here. There's a second order nonlinearity and third order nonlinearity. They're very small, but with the development of lasers, they have become very important. Now, so if you take one of the quadratic terms, and if you launch an electromagnetic wave at frequency omega, then you find that the nonlinear polarization has a term at frequency 2 omega. And this is the source of the electromagnetic wave at frequency 2 omega. Because polarization is nothing but oscillating dipoles, and these dipoles radiate electromagnetic fields. And so there is the generation of second harmonic, which is the 2 omega field. So that's a picture from Optics and Photonics News, how laser launched nonlinear optics. So here you can see a red light coming in and becoming green at the output. So you can understand the process as if there are two photons at frequency omega merging together to form a single photon at frequency 2 omega. And in this picture, this is a quantum mechanical picture. In this picture, I need to also conserve momentum of the incident photons and the exiting photons. And we find that this essentially implies a phase matching condition. This condition, if you calculate, we find that the refractive index at frequency 2 omega and the refractive index at frequency omega must be the same. So birefringence is primarily used for phase matching, but currently the most important technique is quasi-phase matching, where you use a periodic modulation of nonlinearity along the propagation direction to overcome the phase mismatch. Now, we have seen red converts to blue through the nonlinear polarization term. The question is, can I convert blue to red? The other way around. The same nonlinear medium, instead of input red and coming out with blue, I input blue and can I come out with red? So let me go back to the nonlinear polarization term. And if I take an electromagnetic wave at frequency 2 omega incident in the medium, the nonlinear polarization is at 4 omega and not at omega. So there is no nonlinear polarization at frequency omega. And hence, classically from Maxwell's equations, it is not possible to generate omega from 2 omega. But it is found in an experiment that if you launch a fundamental at 655, for example, you come out with frequencies around 1310 nanometer, which is double of this. And this is an experiment which was conducted by the Nice group. Here is a quasi-phase matching, periodic domain reversal. And you can see, depending on the period of the domain reversals, you can generate different pairs of frequencies, all of them satisfying energy conservation. So here what is happening is, unlike the second harmonic, where two photons merge to form a single photon at frequency 2 omega, here one photon at 2 omega splits into two photons of lower frequencies. And this is called spontaneous parametric down conversion. It's a spontaneous process exactly like spontaneous emission. And there is no classical explanation for this. You need quantum mechanics to explain this process. And it is interesting that the emerging photons are entangled in different degrees of freedom. It could be polarization, it could be time and frequency and so on. Now, at the same time, if I put input at both omega and 2 omega, then the nonlinear polarization becomes the sum of these two electric fields squared. and I find there is a term at omega. So all it implies is that if I choose at the input both 2 omega frequency and omega frequency, there will be a nonlinear polarization generated at frequency omega, which means that this nonlinearity now can generate this frequency omega, which will actually add or subtract from the propagating electromagnetic field at omega. So classically, if I put both inputs at 2 omega and omega, then it is possible to generate omega further, and this process leads to what is called as parametric amplification or attenuation. So if I had only 2 omega at the input, there is no nonlinear polarization at omega. But if I put 2 omega and omega, I have a omega nonlinear polarization that leads to additional electromagnetic fields at omega. So this is a parametric amplification process in which I have a nonlinear medium. I input frequency 2 omega and a signal at omega frequency, and the signal gets amplified or attenuated depending on the phase of the signal. So this particular amplifier has very interesting quantum properties because essentially this whole entire process, down conversion process, is a quantum mechanical process. Now, one can actually use Maxwell's equations and get two coupled equations coupling the electric field at omega frequency and electric field at 2 omega frequency. And if you solve this equation with inputs at omega and 2 omega, with input conditions, for example, amplitude of the fundamental with amplitude E10 and phase, amplitude and phase of the second harmonic, then you find that the solution of the equation comes out to be of this form. Very simple solution. And it's interesting, delta phi is the phase difference phi 2 minus 2 phi 1. Phi 2 is the phase of the second harmonic at the input, phi 1 is the phase of the fundamental at input, and there is a phase difference phi 2 minus 2 phi 1. If I choose exponential I phi such that delta phi is pi by 2, then the cosine and sine hyperbolic terms add and to give me an exponential amplification. If I choose delta phi is minus pi by 2, then the cosine and sine hyperbolic subtract from each other and I get an exponential attenuation. This is the phase sensitive part of the amplifier. Depending on the phase difference between the pump at 2 omega and the signal at omega, I can either amplify the signal at omega or I can de-amplify the signal at omega. This is called a phase sensitive amplifier, and this particular amplifier one can show through quantum mechanical arguments. It adds much less noise than a conventional amplifier such as erbium broad fiber amplifier, for example. So here's some initial experiments which I picked up from the net. And here you see the without the pump, you have with the pump, depending on the relative phase between the signal and the pump, the amplification is either amplified or de-amplified from plus 5.3 dB to minus 3.4 dB. So it's very shows the very sensitive phase sensitive nature. In fact, there have been recent experiments to look at using these phase sensitive amplifiers for communication because they add very little noise. And you can see here with these experiments, you can extend the reach from 800 to 4,500 kilometers. And that's a significant increase in range by using these kind of amplifiers, quantum amplifiers, which do not add much noise to the amplification process. Now, it's interesting that because this is a purely quantum mechanical process, if I don't put any input, if I don't have omega input, I have only 2 omega input, quantum mechanically, there is nothing like no input. There's always vacuum fluctuations. So there are vacuum fluctuations entering the nonlinear crystal at frequency omega. And this omega and 2 omega mix together to generate an omega frequency at the output. So this is called a squeezed vacuum. So you put nothing here, radiation vacuum, and out comes some signal, and that's called the radiation squeezed vacuum. And what is interesting is, if you look at the light coming out of this this particular process, it has a noise which varies with time. This is for a vacuum state in which there is no photon in the state. So you see electric field fluctuations with time. If you have squeezed vacuum, then you have an amplifier, an output which is time varying. And here you can see at these intervals of time, the noise is much less than in a vacuum state. So this particular squeezed vacuum is very interesting. It is used for increasing sensitivity for interferometry and applications in LIGO for gravitational wave detection, because you can use these intervals of time to measure the signals with much less noise than with vacuum with nothing in. As I was mentioning, the generation of these two photon pairs need not be at the same frequency. You can split an input photon, which I've drawn as a blue line here, into a pair of photons of two different frequencies. The sum of these two frequencies must be equal to the input frequency. Now, we have done some work on domain engineering of a crystal, which is such that the horizontally polarized pump photon can split into a pair of red and green photons with combination with green vertical and red horizontal, or red vertical and green horizontal. So both these processes are equally probable, and according to Feynman, when you have both these processes indistinguishable and impossible, the output is a linear combination of both the paths, amplitudes. And so what you find is the output is a linear combination of these two possibilities, and this output is actually a polarization entangled photon state, which has very, very interesting application in today's quantum information technology science. Because Professor Kehar Singh has been working in the area of holography for a long time, I just happened to see a paper just a couple of days back on using these entangled photon pairs for holography for increased sensitivity and resolution, even in the presence of noise. So what's actually happening is these polarization and spatially entangled photons are illuminating two different screens. One of them contains a phase object, and you do intensity correlation rather than amplitude correlation, which is done in normal interferometry. And you can get much better signals resolution, and even in the presence of noise. This just came out in Nature Physics, May 2020. I would like to end by saying that parametric process is a process in which a single photon gets into two low frequency photons due to the nonlinearity in the crystal. This has applications in parametric amplification. Although parametric amplification can be explained classically, it's a purely quantum mechanical effect. The process can also be used to generate squeezed light, and this is for enhanced sensitivities, interferometry, spectroscopy, microscopy, and so on. It has very, very interesting applications. In fact, people do imaging without interacting with the object, non-interactive measurements, and there are people investigating this for use in microscopic applications. So you can generate entangled photon pairs. Entanglement can be in different degrees of freedom. It could be polarization, it could be frequency, it could be spatial mode, etc. And this is today finding application in cryptography, quantum computation, and of course testing of some fundamental hypotheses. And this parametric process is also a source of coherent light, and this leads to what is called as parametric oscillators. Thank you very much for a patient listening, and if there are any questions, I'll be most happy to answer.
Thank you, Tyagarajan. Great on time and very nice lecture. So if there are any questions? Yes? Somebody has raised a hand.
Ritvik Das.
Yeah. Okay, Ritvik.
Yeah, Ritvik.
Thank you, sir. Thanks a lot for the talk.
Hey,
it was really nice hearing you after a long time. Just one small query I had is it? We were talking about a single frequency radiation incident and carrying out a degenerate down conversion, right?
Yeah.
So what about incidenting a pulse? If it's a temporal envelope, does it automatically classically could be explained, or a semi-classical explanation, or still it will require a quantum mechanical interpretation?
No. So the pump, actually, first of all, there cannot be a perfectly monochromatic pump. So any pump we take will have a spectral bit. So this is for an explanation, but if you take a pulse, you'll have a spectrum. And that spectrum will lead to generation of photon pairs over a range of frequencies which are different from a continuous wave pulse. So for amplification process, classical explanation is perfectly right, except if you want to really calculate the noise figure of these amplifiers, you need to use quantum mechanics to show that actually a parametric amplifier has 0 dB noise figure. It doesn't add. You can make sure that the parametric amplifier adds 0 dB noise to this amplification process. But so people have shown 10 dB improvement in amplification process, in noise properties.
Okay.
But for squeezed vacuum, you have to have a completely quantum mechanical picture. You cannot explain using a classical picture because there is no way you can generate omega from 2 omega using nonlinear polarization. If that answers your question, Ritu.
Yes, sir. Yes, sir.
Okay.
Thank you.
Okay. Thank you.
Thank you.
Any other question? Okay. Then we actually have come to the end of this session, but there is no break. So we continue with the next session now. And the first talk is by Dr. A.K. Gupta. So, Dr. A.K. Gupta, are you able to share now, or Joby will share? अनम्यूट कीजिए पहले अपने को.
Yeah. I will try my.
Okay. So Dr. Gupta did PhD with Professor Kehar Singh. He was director of IRD, and when I was doing my MSc project, he was doing PhD. So we have known since then each other. Share हुआ नहीं है अभी.
I think it is coming, but maybe net problem. अभी नहीं आ रहा sir, it is delayed. So, in that sense, maybe I can share.
Bahuguna, you want to say something or you have raised a hand?
No, I am able to.
आ गया.
Okay, आ गया. Okay, fine. प्रेजेंटेशन मोड कर लीजिए अगर हो सकता है.
Presentation. That's okay. Yeah, you are able.
Yeah, but your voice is breaking now.
Now, okay. It's okay.
Yeah, continue.
Yeah, okay. Good morning, everybody. I wish and greetings to Kehar Singh sir. On second birthday, and he has been source of inspiration and have long since 1972, and he had motivated throughout my career. Now I am dedicated, still I am taking guidance. So today I will discuss program I did at IRD, radio photonics program. Professor K was the teacher for this program, and he has been associated with this program right the conceptual stage up to the final. So we initiated the program on micro-optics, nanophotonics technology, and there are four. I will present the review of work carried out at different centers. I was the facilitator. I have not done the publication of the project, but was having to initiate the programs in our country because as far with the electronics, nanophotonics are gaining importance in the science, and they are of application. And globally also, in nanophotonics, even the laboratory scale only, not commercial application and commercial devices. So 2000, I thought it was right time to initiate the program of this nanophotonics technology in the country and do something science application. So nanophotonics is quite different from conventional optics photonics.
Sir, we are still in the first slide, sir. Have you moved the slide?
Hello, I am able to move the slide. I am able to. Yeah. So we started the work on micro optics, yes, photonic photonics, materials, quantum
Sir, the slide has not moved here, and your voice is also breaking.
I should be clear.
Maybe I will share, and you can speak. That may be better, sir.
How can I do better? I
वैसे ही कर लो. I think bandwidth बहुत limited है उनकी.
इसलिए problem है. Sir, you can unshare, and maybe I will do the share.
Okay.
Because
how do the
जो भी आगे चला गया तुम्हारा.
Okay.
Now you are
Share again.
Yeah, I'm sharing. I'm sharing. Is that okay? Is it visible?
yeah.
Yeah, now it is okay.
Yeah. So
Make it a slideshow. Yeah. Okay. Fine.
previous slides. Previous slides.
नहीं तुमने बहुत बड़ा कर दिया ये.
Okay.
स्लाइड शो नहीं है.
Yeah. Next slide.
अब ठीक है. Yeah, this okay now.
Yeah. So we started the micro optics, nanophotonics, photonic crystal materials, photonic detectors. Was not possible to work it alone at IIT, so we collaborated with many academic institutes which are interested in these areas, and we were doing some work in the country. Micro optics, IIT responsibility alone, metamaterials and Kanpur responsibility. There were many centers interested in photonic crystals, IIT Kanpur, Bangalore, and IIT initiated the work on photonic crystals, and I was asked to work on photonics and quantum IIT Bombay started doing it. Next slide. Next slide.
Yes.
मेरे ख्याल से आप अपना वीडियो भी बंद कर लीजिए, खाली बोलिए. That will be then probably bandwidth will be better.
So here the micro optics applications slide.
So micro optics actually when the adaptive optics, even the lens that actually could not procure from abroad, and we were sort of difficulty. So we thought that the micro optics we can what we require for adaptive optics, and we already requiring a lot of optics for our thermal imaging system. So we also in the computer related program. So we established the computer test facility at IIT for micro optics. Micro optics cannot be fabricated with the conventional. The only thing, lithographic techniques, mass lithography, micro cleaning, all these techniques are needed to develop the micro optics. Micro optics vary in size from about micro size to the millimeter. So we developed the fabrication techniques, many techniques for development for the fabrication. All tests were created at IIT, and we developed the micro array, what is required for optics application. 16 by 16 micro array on both at fused and substrate. We did next slide. We also created the computer generated program we require for our optics in thermal imaging medium, and we could generate a generated program, replicate 5,000 elements, 1,000 elements, and it is 40 mm by 40 mm. And what we found the results, whatever the results got to the spherical terminator, similar results got from the computer generated program. So whatever the landscape what could fabricate the IoT, that also are with what we got from the professor they have got, and that also could fulfill our application for optics. Now we are developing the wavefront sensor technological application around our array developed by next slide. Next area is the photonic crystals. The photonic crystal again the structures they are very special property, and they and photonic photons interact with material analogous with electronics interact with semiconductors. So electrons what do in periodic potential the photonic band gap do the same purpose, fulfill the same purpose, and we create a defect in band gap. We can create the special property. It can act as a sensor, and so many special properties we can create. Next slide. Next slide. I will present only achievements of the different sectors. It is discussed in the detailed results. IIT Kanpur developed the application technique 1D and 2D by self-assembly and lithography. They worked on the filters, sensor for reflection from lasers. They developed the techniques for full cell efficiency, and they developed the laser photographic structure. I see below they have developed in a silicon cantilever with 2D crystals. They dedicated a microwave uniter, generating the wavelength function of. They could develop a force sensor for biomechanics. IIT Delhi Joby has a wonderful experiment using the multiple interference photography. He fabricated a 1D, 2D, 3D photonic structures, and he has got a very beautiful results. I'm not able to present it here. Sorry for that. But, all the structure the application, I think is for bioscience. Metamaterials are popular materials many times because of their close and they have a different test. So one can generate a flat lens out of the material structure. They are artificial structure less than the wavelength, and they very important application in defense because of the cloaking or hiding the. I think defense was much interested. So though it was a long dream, but somehow at Kanpur, Shakram not develop the material structure, a camouflaging application or camouflaging of our target in near infrared, infrared, and long wave. He also the mathematical structure at sensitivity nanometers. But main challenge with the mathematical structure to prepare this structure on a large scale, and that if it can be wrapped around the a target, it should be unflexible. Next slide, please. So I think previous slide. Yeah. No, previous material. Yeah. So I think recently only last year, I think he could generate the material structures on the flexible states at the mostly at polypropylene, and that also I think 100 millimeter by 100 millimeter structure where they consist of thousands of material structures, and in the near and middle and far long wave in and I think with the DRDO is trying this material structure on a very large scale so that it can find applications for defense. Next slide. Promising applications of yes, for countermeasure application of defense, but the problem is that you should be able to fabricate large area, techniques expensive, and the environmental issue. So this is a challenge. They should the specification what we require. So that is to prevent. Otherwise, the making the structure on the last phase, that problem. Next slide. Silicon photonics is another very challenging area. I think where so far we are using the optics, the linear optical materials, but integrated in silicon photonics, we integrate the optics and electron silicon chip. So far, scientists could not work to fabricate the optics silicon for the indirect material. It is very difficult to integrate laser the laser structure in the but eventually to increase the data speed, silicon photonics are lost. So people at Intel, at IBM, scientists started working. They got message, and based on that message, we also thought hard work at the in our country, India. And so I created the facility. Professor Bijoy, I think he could make the fabricate fundamental components, photonic wiring, ring regulator, ejector regulator, all these devices you can create from the silicon. And next slide. Yeah. So based, he did not stop in DRDO. He continued further research with the rest of DSP and MIT. And now you can see the silicon photonics integrated circuit are finding application, quantum logic, some solution, 5G communication, neural network, lab on chip, optical interconnect, and this advanced all these applications, this is being used. So he got a very major result from MIT, and he also started private industry in Bangalore. And next slide. He's working on the FPGA. This is the full gate array. This is equivalent to a FPGA adapter. You can program many function optical functions on a chip where you can find a silicon and this objects. And so I think it just initiated, and 4-5 years hence you can see a optical FPGA. Next slide, please. I think he's
Dr. Gupta, 1 or 2 more minutes more. Yeah.
Okay. So next slide, please. So detectors that Bombay has worked, they could show the demonstration for 2 to 5 detector and M2 micron detector on collective detector of silicon substrate, and he could do, I think he worked on about out growth samples. Somehow cannot do the structure because he got the NP, but he demonstrated that action. Next slide. IIT much more terahertz technology, and another important unexplored area. So we are
होना चाहिए। चीमा साहब, जितना शोर पाकिस्तान ने मचाया फलस्तीन के लिए, उतना किसी और इस्लामिक कंट्री को हमने नहीं देखा कि वो आगे आई हो और या उसने बात की हो। यहाँ पे तो आम लोग भी आपको पता है प्रोटेस्ट कर रहे हैं, सब कुछ है। लेकिन एक चीज मुझे बताइए कि जब कश्मीर की बात कहा जाता है कि पाकिस्तान कश्मीर के साथ खड़ा है।
Next slide. Next slide. Yeah, so IIT had developed a ring terahertz oscillators and injection seeded traveling condition. So we had detected terahertz 1.8, 2.5 terahertz frequencies, and in linear optical communication, we have also detected the capacity of terahertz range, and at present the IIT developed a terahertz for defense. Next slide. Next slide. Yeah, so in conclusion, I would like to say that we have scaled the base of nanophotonics technology at various standards, and technology is already existing to drive a program and the academic group required support major of the industry so that it can move to the commercial application for defense application. For silicon photonics, MIT is taking a lead. For materials, DRDO and even for arts, you are taking the lead to then create the defense application. So for other areas also, I think somebody will talk about derive the photonics and technology put forward school application. Next slide, please.
Okay. Thank you, Dr. Gupta.
Thank you very much. Thank you for all the coordinators. And I have presented the work on a period.
Yeah. Okay. Thank you, Dr. Gupta. So, any question? Quick question. Okay, if not, then I move on to Dr. Chanchekar, Professor Chanchekar. Chanchekar, you can share the slides. So, Professor Chanchekar did his MTech project with Professor Kehar Singh, you know. After that, he moved on to PhD to IIT Madras, and then he came back to IIT Delhi as a colleague. He's my classmate from MTech.
हेलो हेलो
हाँ शेयर कीजिए अपना
हुआ शेयर नहीं हुआ
नहीं अभी
शेयर और
वो जो एरो बना हुआ है ना ऊपर
या तो था भी
क्या हुआ
हेलो
हाँ चंद्रशेखर
हाँ शेयर हुआ नहीं हुआ
नहीं हुआ ना अभी
नहीं
शेयर स्क्रीन करके फिर चलाओ
जस्ट वन मिनट share screen is not coming on this.
No, you are already a presenter, sir. आपको आना चाहिए.
हाँ. Now is it coming or not?
No, sir.
No, sir.
Sir, next to leave button, there is one arrow.
Yes, I am seeing that. I am pressing that.
Yeah.
आप प्रेस करके आप स्क्रीन वाला वो विंडो में प्रेस कर लीजिए.
वो कंट्रोल शिफ्ट ई करके ट्राई कीजिए. कंट्रोल शिफ्ट ई.
कंट्रोल एस.
नहीं कंट्रोल शिफ्ट है ना एक. कंट्रोल शिफ्ट एंड फिर ई.
तीनों में एक साथ.
Just 1 minute. Screen should come, na? Share screen. That is not coming.
हाँ आ गया सर. आ गया.
आ गया.
हाँ यस.
अपना वो चला दीजिए. प्रेजेंटेशन चला दीजिए. हाँ ओके. Yes.
Is it coming? Is it coming?
Yes. Good. Yeah.
First of all, I will like to say to Professor Kehar Singh for a long, healthy and very useful life in future. As Anurag told, when I started my MTech, some time before that, Professor Kehar Singh came from UK and he did some experiment on vibrations in Imperial College. I saw that later on, but at that time also I saw. Here with him I started working on laser speckles, but by taking the cue from that experiment that he was working, he did some work, initial work, and demonstrated some vibration pattern on a plate. Later on it was found when I was working with BHEL that if properly analyzed and used, a analog holography is very useful for designing the bladings. So today I will be talking furthering that work, that type of work on measurement of temperature distribution, heat flow, and heat transfer parameters by using holography. Holography means digital holography because linear holography, no, sorry, analog holography or conventional, what you call it, is very useful technology if you use in the form of technology. But to get the information from it is tedious task. So digital holography, if you design properly, write your programs properly, and you want a limited information to get, is very useful, very fast, very accurate, very precise. By seeing that, I will not talk about the mathematics. Whatever mathematics part is there, I will just skip, but I will be talking about how it can be made useful for industries, for industrial measurements. That is what I am going to talk. This is a flow diagram for that, how digital hologram is recorded and reconstructed. You can see here that you record the hologram in a conventional way, but you reconstruct it by using numerical techniques through computers. That is why you are calling it. It is not completely, recording is not through computer. Recording is conventional or analog, but then you are converting it to digital form. And that digital form, once you convert it, you take it in your computer, and it becomes very easy, very fast, very accurate if you have written your programs and you have used your reconstruction mechanisms correctly to reconstruct or to find out, to calculate your parameters very precisely. This is just how to calculate the phase difference, but I am not interested at this time. I will be talking about certain experiments which are useful for industrial measurements by using digital holography. Why digital holography? Why not analog holography? Because analog holography, if you do the interferometry, gives you the phase difference only. And here in digital holography, you can measure both amplitude and phase, and by that you can make a phase map, which will give you a very fast picture like DSPI. We were working on DSPI also. So this is the one experiment where it can be used to design the wires or to bring down the cost of the wires, which carries the high currents on high voltage lines. By keeping that in mind, this thing was done, and then it was found that you can calculate from here with this experiment. It is showing a vertical, you can do it horizontal also. In any way you like, you can calculate it. So you can calculate with the help of this heat transfer coefficient and thermal conductivity at the surface of the temperature of the wire. You have made an interferogram. This is the interferogram, first picture is showing. Then you can make a phase map. You can calculate the refractive index and then temperature around it, and then by using the proper equations, you can find out how much is SC, how much is cumulative, how much is a conductive heat transfer coefficient, and how much is thermal that. So you can bring down by doing proper studies, you can bring down the cost of manufacturing, that how much thickness should be there, how much other parameters should be there of that wire which carries the high currents on high voltage lines. So this was, I have not shown you the vertical, this horizontal, because that is a property of a firm. They don't want to disclose it how that thing is coming, but I have shown you the vertical. Similar way, it will work for the horizontal also. So this is how you can minimize the cost of designing, and then a design is done to minimize the cost of manufacturing and for a long life. Of course, any design which will not be helpful for the component to live its full life is not supposed to be very useful. You can see here how with height, the conductive heat transfer coefficients is varying. You can calculate it very, very precisely and see it. This is the way how you calculate it. You record one hologram, record another hologram, take the Fourier transform, make the phase map phi1, phi2 for one, then subtract it, then unwrap it, then use the Abel transform for evaluation of this, then calculate the temperature gradient, and calculation of this. All can be done in a computer by writing a proper computer programs, and can be done very fast, quite accurately. Of course, many things which you can do in analog holography cannot be done in digital holography, but still for industrial application this is a very good tool if system is designed and your computer programs are written very nicely. This is how you can see it. So it is a local convectivity transfer coefficient for wire different diameters. You can see the different diameters, you can calculate it, you can see what is happening. A qualitative also you can see, and quantitative also you can calculate. So one can actually get everything what you need for designing such type of systems. Then for space applications, because there you need a very high class of fidelity for electronic circuits, electronic components. A lot of heat is generated while you use these components for a long time. How to dissipate that heat, how to optimize, how to minimize the failure of the component. You have to make a zero failure of these components or these circuits which go in a space. So we did, based on that, some studies, and which are found to be quite useful in that. Here you can see on the left side, here is a system, digital holograph system. You can see a interferogram on a computer screen, and then you can see different type of fins you can use to transfer the heat so that component is not overheating. You can see the interferograms, and by seeing that interferogram you can get fairly good picture, but you can calculate them out. Everything you can calculate them out, that how the temperature is varying, how the heat transfer is being taking place, how the temperature gradient is there. By seeing that, one can tell how this heat sinks can be designed, or which heat sinks is most suitable for application in space, or for those industrial applications where you have to shut down your where you don't want to shut down your system for a long time. You can see for the many, by taking many heat sinks, very large number of experiments were conducted, and then it was concluded how a design can be optimized. This type of investigation is very useful to minimize the failure of the electronic components and electronic circuits for industrial and space applications. Then nowadays, a micro powering systems are being used for many applications, for drone, etc. We conducted many applications for that, but one I am showing it to you. Of course, it can be used for a normal flame also, but I have shown it to micro flame because it is very critical and very difficult to make micro flames stable. So how it can be made stable, how you can use the magnetic field to make it stable. This is a similar type of digital holographic setup where you can keep a micro flame there, and then you can see here the interferogram of the micro flame, and then in different positions of the magnetic field you can see how magnetic field affects the combustion of that and how it can be stabilized, because micro flames are very unstable flames. You cannot, it is very difficult to make them stable. So here you can calculate out the from this interferogram, you can make a phase map, and then you can calculate the refractive index distribution, and then by using the Lorentz formula and of course Abel transform to find out the temperature and temperature profile. You can find out its temperature profile, and then you see the advantage of this method is digital holography is that you can do all these experiments in a very short time. By using analog holography or conventional holography, all these experiments can be conducted, I feel, because I started working in that. But it will take a lot of time, and it is very cumbersome to use, cumbersome to take out the data. Here, it is more easier. And once instrument is made or system is designed, it is very fast. Accuracy here can be achieved quite good, and very precise measurements can be made. I'm not telling it will make a more precise measurement than conventional holography, but conventional holography, to make that type of thing will take a lot of time, which industries cannot afford, because engineers' time is very costly in industrial measurements. But here, anybody can do it once you make a system or design a system and give a protocol, do it like this. A conventional holography work cannot be done by everybody. You need a very trained engineer and a lot of time to extract the information, to extract the data. Here, some more things are shown just to establish that thing. That how.
Chandrasekhar, you have just 1 minute or so. Okay.
Okay, fine. So you can see how you can stabilize the information by using the magnetic field and by using the digital holography. Then another thing is how you can see the convective heat transfer coefficients or laminar free convection flow in water. You can see that is useful in chemical industry. And one more thing I will like to show you, how you can see the diffusion coefficient in visible transfer, this in transparent fluids, which is very useful in medical industry. You can all see them in very short time, very precisely, very accurately by using, because Anurag is having less time, so I will cut down and very fast I will do it for you. So here you can. Okay. So here you can find out diffusion coefficient online, almost online. Almost. It is not, let me tell you, it is not online by like conventional holography, but it is almost online. Almost online in milliseconds you can do it. So here you can see the type of information, and in conclusion I can say to you that digital holographic interferometry is an effective and powerful tool for a range of applications used in measurement of temperature, heat transfer, and heat transfer studies in industrial applications. Thank you very much.
Thank you, boss. Thank you, Chandrasekhar. So, any questions? Iqbal Hussain, I see your hand raised. Is it by mistake? Okay. I think we'll move on to the next. Thank you, Chandrasekhar. You can unshare now, and we move to Dr. Kantpal, HC Kantpal. Kantpal?
Yeah, I am here.
Yeah.
And I will mute both camera and this camera, and then keep on presenting,
Yeah. No, but
so
but you have to speak, so you don't mute yourself.
No, I am not muting myself, but I'm chairing now. So has he taken out his presentation, Professor Chandrasekhar?
Chandrasekhar, have you unshared?
No. You can.
ये किसका है पता नहीं है, ये
चंद्रशेखर
का ही है. चंद्रशेखर
चंद्रशेखर का ही है.
ओ चंद्रशेखर अपना अनशेयर कर दीजिए.
Stop presenting.
चंद्रशेखर
Okay.
Okay. Yes. Kanpal ji aa gaya. Okay. Yeah, please go ahead.
Okay, I take first of all this opportunity to congratulate Professor Kehar Singh sir on his 80th birthday and dedicate this talk to him. He has been a source of inspiration for me for last 30 plus years. And you know that whatever I would be talking in the evening. Now I would be walking you through the futuristic approach in the industry, especially in LED lighting industry, where we have been thinking to go about these various topics which I have shown in this slide. First of all is human-centric lighting, then laser-assisted remote phosphor lighting, that is called LARP. Its application in home lighting is being shown. Initial strides have been taken by Professor D.S. Mehta at IITD. Then nanoparticle doping lighting, which we had a joint hand. I'm in FAM Industries, by the way. So FAM Industry joined hands with IITD with Professor Bhaskar Kanseri. But I will tell you later on what happened to it. You know, then nowadays people are talking of driverless driving, and the sensors are coming in a big way for making this possible. And finally, I would be talking you through the much talked about this, neutralization of COVID-19 virus through LED UVC disinfection and all that. So first of all, what is being thought that because the life has confined itself within the four walls of offices, houses, industrial houses, and all that, and because of the being confined inside the house and not getting the daylight throughout, for a long period of time, human activities are going down day by day, and it is being thought that now LEDs should be lighting should be done in such a way that it mimics natural daylight for enhancing the human performance and all that, because all this biological activities are balanced by daylight, natural daylight. So LEDs are going in a big way, because the function of daylight is that it depresses production of melatonin, therefore rises alertness, and this what is called the circadian rhythm. It depresses the need for sleep. It controls the certain hormones which are for balancing the immune systems and bring happiness to make life more enjoyable. So the need is to make life possible within the four walls, where whatever has been written in this slide, that we can have motivation, concentration, productivity, mood, sleep, well-being, and activity, which are otherwise dying almost day by day by the remaining the life being confined inside the houses. So it is being thought that the light which has to be there inside the room should be tunable in the full day cycle. It should be app controlled, and there should be no switches so that the disturbance doesn't take place. And what is being thought is that this daylighting can be controlled three ways: spectrum, intensity, and timing. That throughout the day, when sun moves from morning till in the evening, the spectrum keeps on changing, and depending on what color temperature you get, you get different type of activities, because spectrum, different wavelengths affect human being in a different way. Therefore, spectrum has to be tuned as per the need of the day, which I will show you in the next slide, as shown here in the right hand side, that the spectrum looks different at different times of the day. And then the intensity of the light within the rooms should change automatically, because the circadian effect starts at light level of 30 lux and saturates at 1000 lux, and after that nothing more is required, and elderly people require more of light for the same type of activities to be maintained, you know. So this is the slide which shows the 24-hour working of the brain of a human system. And here the light inside the room should go this way, that from cool white light in the morning to wake up time, it should be cool daylight, which means that its color temperature should be 6500 Kelvin. In the daytime, at the lunch time, since it is a relaxing time, the temperature, color temperature should be 5700 K. And after eating, you know, then there is some laziness which comes to again excite the body, and so that it comes to activity again. Then it has to be white light, and that's 6500 K. But after 6 o'clock in the evening, there should be no white light, so that you do not have the stress of having a harder sleep. So it should be warmer white light, something like 4700 K, 2700 K to 7000, 4700 K. So this is the 24-hour duration cycle of human, brain and body. And this has to be kept very active, so that the circadian rhythm should not be lost, you know. And this slide shows at different hours of a day. On the left hand side, I have shown that the timing at different hours of the day. And right side, I have shown the CCT, correlated color temperature. Minimum amount of lux should not be in any case not less than 350 lux, which otherwise is just missing in all Indian homes. And in order to remain active throughout, this is the slide which is talking of the activity to be maintained properly. And this slide talks of the temperatures to be varying from morning till late in the evening, you know. So this is about the human-centric lighting, which is being talked about in industry in a big way, so that all the homes, offices, and could be lit with this. Now the second thought, where we had FIAM industry had a join hands with the National Physical Laboratory. I will be talking about the automotive part, because nowadays high-speed vehicles are coming, and for example BMW and Audi and all that, where the speeds are more than 250 kilometers per hour or so. So in order to make the driver see the roads properly, something like the intensity of the light at the source, for example headlamp in the automobile, should be more than 2 lakh candela, so that enough illumination on the road goes when it illuminates the road. And as a result of that, the driver should be able to see the road properly. And requirement is about 11 candela per meter square. That is the luminance value, which on the other hand, nowadays we are getting hardly around 1 candela per meter square or less than that, so that there are so many accidents taking place. But this NPL was given a fund by FIAM, where the first task was to develop phosphors, and these are the different phosphors which have been developed for the need according to the automobile. And the next step is to prepare and this what is called prototype headlight, where the sufficient amount of intensity could be produced, that is more than 2 lakh candela of intensity of the headlamp. And now, depending on where the source will be put, you know, whether it will be inside the headlamp or tail lamp or whatever it is, whether the driving beam has to be operated or the passing beam has to be operated. We have seen it in a different mode. This is transmission mode. White light is produced here on the extreme right side of the upper portion of this presentation, and lower side shows the spectrum which remains stable for more than 10 hours of operation, sustained operation for 10 hours. And the next is the reflection mode. So these geometries will be set according to the need of the vehicle, And here that stability of the light you can see, and the illumination which is being produced is very high as a result of the phosphor being excited by blue laser, blue diode laser of 455 nanometer. And then this is the comparison. This slide shows the comparison of two lights. This is the in between this B and FR, the transmission mode and reflection mode, laser excited phosphor light, and here on the extreme right below, it is the LED light, so you can have a complete change in the intensity of the light. Now another this topic was in my mind from my days in NPL, but somehow it could not take a shape in when I was in NPL.
Kanpalji, just 1 or 2 minutes more.
Yeah, I will finish in a day. But now it is being looked after by by Professor Kanseri of IIT, because this is very important topic and it is being talked in industry, so that we can have tunability, we can have angular adjustments of the lights in the tail light, especially of the automobile. And now, as I told you that we are talking of autonomous driving, that is called driverless driving, and NIR LEDs and FIR LEDs are the future in order to have the detection of the obstruction on the roads and all sort of the obstructions like low speed vehicles and this thing, and they are of value because of low power consumption and being cost effective. And finally, I am talking about the germicidal irradiation of UVC LED. At present, the 253.7 nanometer of the wavelength coming from low pressure mercury lamps are being used for disinfection. But since the phasing out of mercury lamps is going on by 2025, or lamps will go, therefore, what is being talked about is UVC LEDs. And these are the various industries which would be doing utilizing this UVC LED. Especially the important wavelength is 280 nanometers, and another wavelength which is being talked about is 222 nanometer, 222 nanometer, which would be very helpful for disinfecting the viruses, COVID-19 viruses, or different variant of that virus. And finally, whatever is being talked about will depend on how beautifully and precisely absolute measurements are done, and how we provide traceability for all these measurements, especially in case of LED measurements. Thank you very much.
Thank you, Dr. Kanpal. Very important applications. Are there any questions?
There is one R. Parmar who has raised his hand.
Yeah, please. I'd be.
Mr. Parmar, you want to ask a question?
I think.
I'm Ajoy Khatak.
Yes, sir.
Yes. Here.
Yes, sir.
Simple question that for room lighting.
Yes, sir.
For people like us who stay most of the time inside our home, what would you suggest? What type of light do we use? Any commercial brand that is available which you would recommend?
At present, for example, the house where I am living right now, is that we have made provisions that at different times of the day, we can switch on the lights by by switching on the light by using these switches, but it should be automatic, that you should have the exposure to daylight sort of thing automatically. But at present, just it is these type of lights are coming in the market, and
So
you
give me
will
an
find
example.
after some time that one single gadgets will different types of LEDs, where you will get white light LEDs, you will get 5700 Kelvin color temperature LEDs, or 4700 color temperature LEDs. And mostly for the question which you asked, sir, that we need more than something like 600 lux for our working, because we are aging people, and those who are more than 65, everybody should keep in mind that those who are more than 65, they need more than 600 lux of light for the activities to be maintained properly. So at present, this will be very hard, because, mostly in order to save money, we go to LED lighting, which hardly produces less than 100 lux or so. So that has not to be done in any case.
Yeah. One question is, Kanpalji, we have been earlier using, whether it is tube light or other lights, a continuous spectrum of light.
Yes.
LEDs now we have
tunability.
Like, narrow band. Does that affect the human
No,
being?
yes, you are right, sir. We have both types of LEDs, narrow band LEDs. These narrow band LEDs are used for, for signaling, for example, red, blue, and red, green, and yellow sort of thing. Those are narrow band LEDs. But on the other hand, in a house, in homes, offices, and all that, mostly we are using gallium nitride excited phosphors, so that the total white light is coming out. But the problem at present is that the sufficient illumination is not obtained by means of that.
Okay. All right. Thank you. Thank you very much, Dr. Kanpal. Now we move on to Dr. Benjamin Leonel. Benjamin, are you there?
He's there.
Yeah, I just made him presenter also. Yeah.
Sir. Sir, yeah. I am there very much.
Yeah. So you are sharing a presentation?
Yes, sir. I'll just load it now.
Please.
Yeah.
Benjamin Leonel.
Right.
So Mr. Leonel has been, he was our MTech student long back in early 80s, and then he moved to DRDO, and then he was director of IRD Dehradun, and he has just retired on 30th of June. Okay, so today is a free bird. Okay?
Yes, sir. Yes. Good morning, everybody. It's a great pleasure to be with you all today. And first of all, I would like to extend my hearty congratulations to Professor Kehar Singh, and who was our professor when we studied. And it was a very great learning for us to spend our time both with Professor and at IIT Delhi. And I benefited a lot in my career and by whatever I learned from IIT Delhi. And I would like to once again give my thanks to all of you, and in particular to Professor Kehar Singh. In fact, apart from that, when I was director IRD, sir had helped me a lot in conducting the International Conference on Optoelectronics through 2019. And he was the technical chair along with Dr. A.K. Gupta, our former director IRD. And it was a very, very big success, and thanks to the support extended by these stalwarts to me. And with that, I would like to just start this lecture. Actually, we benefited from our student days. There was an optical workshop, and we benefited a lot. And Professor K.D. Sharma was there at that time. And of course, that experience was very helpful throughout our career. But today, I know that there is a proposal to start a Center for Electro-Optics, and I'm very happy that this sort of a forward thinking is there in the department, which shows the vibrant nature of the team of academicians who are there, all of you. And so this is a very good, step. But today I thought I will just touch upon because in my entire career I have had the opportunity to work in the ministry, and I had a very colorful experience profile. I worked with the foreign affairs, I worked with the academic institutes, I worked with the industry, I worked with the ministry, I worked with various agencies of the ministry. So I had a deputation also abroad. So I have a fair idea, and I thought that it would be an opportunity. This opportunity, I will just give a brief on how a center of excellence can work and how to make it as a success. So when is a center of excellence? When I say in this context, I am just pointing to the Center for Electro-Optics in particular, this audience. So when is a center of excellence a good idea? So when there is a need to develop expertise and standards in a certain area of research, and when there is a need to organically develop a new skill sets in a specific domain, and when there is a requirement to innovate and excel in a specific domain, then we start a center of excellence. And as you are all aware, innovation is the key to success. And today, the 21st century, the century of photonics, and there is a huge expectation for a technological breakthrough, and photonics is going to be a leader in that. And but we have to innovate, and it's very appropriate, and it's the right time that IIT Delhi has started this center also. And so what is a center of excellence, and why do you need one? So a center of excellence is a business model, and as you can see here, it provides varied services, and so in our particular case, it will be electro-optics related services, and it has field reps. It requires a set of field reps. Then it requires people to have an outreach. And then you have a contact center, and then you have a HR, and then ultimately the whole game can go only when there is sufficient funding. And so this is a sort of it's a business model. When we call a center of excellence, it doesn't end with only the expertise of the professors or the academicians or the institutes. It also involves other stakeholders in this. And so what is a center of excellence? So what is its purpose and other things? First of all, it enables collaboration to ensure consistency and integration of strategy to activities. When we say this, I would like to clarify that it will have to be a collaborative effort. You cannot have a center of excellence in isolation. It is my experience in DRDO that we did open a few centers of excellence in certain domains, even including nanoscience, in certain institutes. So what happens is once it becomes only a funding by the DRDO, then there is no collaboration, and then after a few years, when the center wants to take certain things forward, there are a lot of questions asked, and it comes to a standstill. So, but it has to be a collaborative effort, not only restricted to a certain funding part, but it has to be a collaborative part. And it has to have provide. That's why we need a good, proper governance framework for this. And it also has to have a clear monitoring of the processes, what we do, the methodology, what we do, and the models, what we follow, and the tools and technology, what we do. So we will have to continuously monitor that. And it also has to have a clear mapping between the business strategy and the projects what the center is doing. So you cannot have them have a business strategy or a focus area or something, and we start doing projects. And so it has to be a highly focused activity, and it has to serve as the focal point for a specific business strategy or a function. In our case, it is the electro-optics domain. And it has to also provide training and consultation functions. In certain areas, they may not be requiring a project activity, but it could require a training activity. It could require consultancy services. And at least with my experience with the Ministry of MOD and other agencies, I can tell you there is a huge requirement. It is only that we have to reach out to the people and tell that we are there. And so this is a very important thing where people are looking for certain consultation, especially in the domain of electro-optics. And also, when the center is operating, you have to have a development and you have to, when you do the development, you have to have a monitoring criteria to define whether it is a success and or where are the loopholes and how we can improve upon it. And these improvements also have to be implemented. And then you also have to have a central repository for the research, holding of IPRs, and then creating the study material so that it can be utilized by anybody who wants to talk to us or who wants to link up with us. Now, how to set up a center of excellence? So whenever a center of excellence is established, in fact, the DRDO themselves have initiated and they have set up a few centers of excellence. But I feel that this is a worldwide recognized model in which first we have to have a strategic alignment between the goals of the center of excellence, their objectives and vision, and this has to be very clearly defined at the beginning. So when we say that, so today we know what is the expertise available in this team of professors who are going to be part of this center. Then we have to very clearly and in a very transparent way, we will have to very clearly define what is our strength area, what are the areas we should focus. We could have a brainstorming and decide that these are the things. Maybe it could be domain specific. We can say maybe for the immediate next 3 years or 5 years, we will focus on this, and then the subsequent 5 years we will focus on. So there has to be a clear strategy when you start a center. Then you have to have an engagement plan. Once you have a clear strategy as to what exactly are you going to focus upon, then you have to have a plan to the different stakeholders. Just now we listened to Mr. Kanpal also. See, there is a business which they are doing, and now if there is a clear strength in the center that we can contribute, we should have a clear definition as to how we will engage with them, what will be the takeaways for them, and then we also should have key performance indicators to measure the utility of our services, and this can be established by periodic reviews, and that is how we can standardize the service. And then when it comes to operating, the center should provide services. It should identify the improvements. It has to be a very vibrant and a dynamic system. It cannot be that you started a center and then you just let everybody do their own, and then after 1 year and see how many projects you have done. That way this center will not go into a road of success. So you have to identify the improvements. You have to continuously see how to optimize the functioning of the teams, how to effectively optimize the sources, resources, the stakeholders' requirements, and then have certain changes adopted, which has to be real time, and it has to be implemented so that we can get an optimum output. So this is a much more detail. I will not go into that. So a center cannot just like that become a big center on overnight. Just by naming a place as a center, it doesn't become a center overnight. First, you have to start exploring to understand the landscape of the requirements, landscape of your domain. How do you fit into the various requirements in this landscape? And then you establish. And it might be initially a few baby steps, very cautiously. Then once we know what are the requirements, then we have certain concepts. Then we do the proof of the concepts. Then we do a course correction to clearly set our strategy and align ourselves to the goals. Then build the momentum and gain ground by doing good projects, improve the strengths and eliminate the weaknesses. And then we can achieve perfection. At that point of time, we'll be called as a subject matter expert in this whole game, and then we win the race. I can tell you with my experience and my exposure with the electro-optic industry in this country, IIT Delhi is the leader. I know that Calcutta University is having, Cochin University is having, Warangal is having, and many people are also starting. But if we focus, I know that we have sufficient strength in IIT Delhi. We have to become the leading agency in the country in the domain of electro-optics. We have all the ingredients for it, but once you put a proper strategy in place, I am confident we'll be able to do it. Now, the current worldwide trend of innovation is that it forms a triple helix framework in which the academics, the business institutions, and the government they combine and they work together to develop innovation. So this is the current this thing, and so the academia will look after the research and the education programs, the students and their placements, and the industry will be looking for high value research projects, and they will also be willing to fund certain projects, and they'll also be requiring, once they fund it, that they must hold the IPR. And another thing would be the students will also get an exposure to work in the industry, and the government is ultimately interested to the economic growth of the country, the development of capability within the country, and creation of new industries, and a potential good workforce in this particular domain. So the academia industry government partnerships is very vital to any innovation in today's context. Gone are the days where academia will work in isolation, and then we go take projects from only the government. So those days are gone. It is a business model which is evolving, wherein innovation is driven by this partnership, in which it is a win-win for all the stakeholders. And the first one was, like I said, the government plays a lead role, driving the academia and industry. And this is the Helix 1 model. And then the knowledge institutions begin to concentrate.
You have about a minute left. So.
Yes, sir. Yes, sir. So these are the various models. And the Helix 3 model is the best one. And this is how they work together. And it is a hybrid of all the organizations. And the combination, it generates the knowledge infrastructure, and it is a beneficial for all the three stakeholders. So the benefits of Center of Excellence is that it can raise the research standards, the training standards, it can boost productivity and address the emerging skill gaps. And also it facilitates partnership between stakeholders, and it enables in the period of time that the Center of Excellence will have sufficient autonomy and to do strategic training and resource allocation and to meet the goals. And the resources will be generated. Once we have set up a successful center, resource will not be a problem. In fact, the center will call the shots and say that we will take this particular project immediately, we will take it particular one later. And this is how it could be a success. And I am hopeful that IIT Delhi Center for Electro-Optics will emerge as a leader in this country, who will become the nodal center for electro-optics in the country. And this will also include collaborative efforts and collaborative R&D with other foreign universities, which I have not touched upon in this. And there is a huge potential for us in this country. And I wish you all the best towards this effort. Thank you, sir. Thank you.
Thank you, Mr. Benjamin.
Yes, sir.
So if there are any questions, comments, you can take. You can unsure this.
Yes, sir, I have done it.
So any questions, comments? I will only say that we look at this advice or whatever you want to say is very seriously, and let's see how we can go ahead with our center.
Yes, sir. Only one thing I will tell, sir. I will tell you only one thing.
Yes, sir.
I mean, since I was there in 83 to 85, our professors, I mean, you were also teaching me. I mean, even they would not have thought what these guys will do once they pass out there. Because in those days, applied optics was not that sort of a domain. But today, the domain has elaborated, and there is a huge requirement. And I think we are in a better position to do great things for the country. Thank you, sir.
Yeah, thank you.
And for the information, we are trying to get Benjamin to the center as much possible after his retirement.
Thank you very much, sir. It will be a pleasure. Thank you, sir.
Okay.
Thank you.
All right. So that brings us to the end of session 2. We are only half an hour late, Joby.
Yes, sir. Thank you for.
Yeah. So now Joby will take over with actually first talk is his, so I can guide that, and then he can take over maybe.
Thank you, sir.
So should we continue, or you want to take a break?
I think we could continue unless Professor Kehar Singh has to get a break. You're okay, sir?
Let's continue.
Yeah, okay.
Thanks.
All right. So the next talk is by Joby. Now we have little shorter talks.
Yeah.
But I suppose these are younger people, so they will have no problem with the connections and so on. So okay, so Joby, please continue. Yeah. So Joby, you all know Joby, so I don't have to say anything. Yeah.
Thank you. So thank you, sir, and happy birthday to Kehar Singh, sir. And I'm going to speak about a topic which is to some extent new to me. And let me see, and some of the slides may be very basic, but I apologize for that. And just let me make it full screen.
You know that you have only 10 minutes total, you know?
Yeah, so I have to finish in 8 to 9 minutes. Okay, sir. So I'm just, this is a question, how thin a lens can be. If you ask this question maybe few years back, you would have thought that a lens can be made thin by making a thin glass lens or combining many, or you may think about Fresnel lens, etc. But what I'm going to talk about is a field which is emerging, which will make a lens to be as thin as your hair. And still it is not a simple lens with all the capabilities of one of the complicated lenses which could be available in your camera or a mobile camera or even best camera having all the aberration corrections or microscope objectives. Can this be made as thin as your hair? That's what the topic which I'm trying to discuss today. And if you look back into a lens, it's a glass piece and it has to refract light and give you a focusing. And lens idea is many centuries back in 17th century BC itself. It is known that lens has been used as a burning glass, and it is the same technology to some extent. Even the lenses are used even now. That is, you have a curved glass and a polished glass, and somehow you combine many glass pieces and to get the best image as possible. And you vertically integrate many lenses to get the best aberration corrections, imaging, etc. But it's the same technology, century old technology in that sense. So even the camera lenses which contain many lenses combined together to give you the best imaging, and even the same thing is in the microscope objective. You have multiple lenses to correct aberrations and give you as much as possible diffraction limited spot size or diffraction limited imaging. So there are many ways you can make it thin, but many of these thin approaches are not good enough because you don't see such a thing in your camera or so. But still you have to go back to the ages old glass techniques to make the best lens. So, but we will need some ideas about Fresnel lens to what I'm going to talk about. So we will need some ideas will be employed from there. But there are other thin lens approaches of diffractive optical elements, Fresnel swan plates, holographic lenses. There are many, but they are not that good enough to replace the best lenses which are needed for any good imaging. So what we need to know is it possible to make a lens with similar characteristics as a 100x microscope objective or a best camera lens on your mobile phone? Can that be compressed to nano dimensions of maybe a 100 to 500 to some kind of a thickness with some features of 100 nanometer or so? Can it replace these complicated lenses? So that's what let's see whether it can be done. How can it be done? And so for that we need controllable nanostructures such that they behave like a lens. So they are meta lenses, and we can use nanofabrication technologies which are used to make ICs and other things which can be used, or even now it is not very clear what will be the best technology to make these meta lenses. So this is still emerging. So we need to make optical elements of submicron or nano dimensions of thicknesses, features and shapes. So that's what will give you finally the meta lenses, and they would be allowed to make optical phase changes. So you have to have introduced optical phases through many unconventional physical principles, not simply refraction or diffraction, etc. So you have to combine many physical principles to make a lens which can work like a very usable lens. And so this lens with similar numerical aperture, similar characteristics of diffraction limited, even beyond diffraction also could be possible using these meta lenses which are in nano dimensions. Also, you can have one single lens or one single element can have multiple functions. Okay, not only simple imaging, you can combine many functions into one single element. So that is a meta surface. So even lens plus other combinations can also be possible using this technology. So if you look at how a lens works, the lens simply focuses a parallel beam of light by introducing varying phase delay across the lens surface. So it is the phase delay is what is needed to make a focusing of light, a plane beam made into a converging beam or converging spherical beam. So it is the same phase delay which is responsible for all the aberrations too. Okay, the phase delay at marginal places give you a spherical aberration, and when light is coming from an off-axis angle, that phase delay lead to coma, and the phase delay for different wavelengths lead to the chromatic aberration. So if you can combine new of these methods, all this can be combined into a meta lens to correct many of these aberrations also. So how to get this required phase using the nanostructures? There are many methods. I will not go into all the methods. I will only touch upon one method, that is the use of nanopillars. So by using nanopillars as shown in this diagram, let's say you have a small glass substrate, and that substrate, let it be of something like 200 by 200 nanometer width. And on top of that, you have a titanium oxide pillar, which is a nano pillar. And when you change the diameter of this nano pillar from, let's say, 100 nanometer to 200 nanometer, the light guided through this nano pillar of 500 nanometer height, for example, then the effective phase of the effective index of that region gets changed. So ultimately, you can make a change of from 0 to somewhere around 0 pi to 2 pi phase shift can be introduced by simply changing the dimension of this nano pillar. So if you plot the diameter of this nano pillar with respect to the phase introduced at the output, that you can see it can. So you can use this lookup table to fill the lens surface. So that is what you will do. So you will fill the surface of the plate with these nano pillars to introduce the phase shifts needed to behave like a lens. So this is how you will do. So you will have a varying dimension nano pillars. So these nano pillars result into graded index variation, and that will redirect the light into different directions. So you can behave, or maybe you can make a prism, or you can make a lens if you change it continuously. So this is how the idea works, by using nano pillars to change the direction of light to get the focusing finally. And so how to arrange these nano pillars? So there also you, yes, I'll finish it. So you can make the surface very similar to the Fresnel lens approach. So you can divide this into various stages of 0 to 2 pi phase variations, and use that lookup table to convert surfaces into the form like this, and finally you can make a lens out of that. So these are some of the very important works available in literature. So you make these nanopillars arrange to make a polarization insensitive meta lens in visible wavelengths, and this shows, for example, on top of a camera, just CCD camera, you put this meta lens to get very good imaging, very similar to that of a high quality lens. And this is the imaging in IR wavelength. And there are many other methods also to make these phase delays. One I discussed was nanopillar. You can also use fin type of arrangement. You simply rotate the fins, and different direction of rotation will lead to different phase shifts. And so that works only for circularly polarized light now, but effectively it can also be used. Other nano antennas methods, there are many methods, so we will not go into those details. So the work which we do right now is to make this nanopillar and nanopillar based method to make a meta lens for stimulated emission depletion microscopy, where you can combine both conversion of Gaussian beam into donut beam, and also to get diffraction limited spot size for microscopic application. So this work is done in collaboration with Dr. Amit Agarwal of NIST USA. So this is the final pattern which will be fabricated through E-beam to make a lens. So there are this last but one slide. There are many advantages why we should go for this kind of meta surfaces. Fabrication methods are very similar to lithography methods, but still they are not optimized yet. But effectively, they are very compact, lightweight, and offer many applications. Not only lens, you can make waterwave plate, you can make various holograms, you can make various optical components out of them. So I'll just acknowledge my students who are working in this topic and Amit Agarwal, who is my collaborator. So thank you very much for your attention.
Thank you, Joby. Any questions?
Yes, sir.
Maybe I can do a very quick question. How do they compare to green lenses?
Like, no, green lenses can never reach this dimension. Also controlling all the aberrations and all together, it can be done, but principle it is similar, but it is nano dimensions. That's the main difference, and it's much more possible. Things are possible in future. It is the emerging technology.
Joby, I have a comment.
Yes, sir.
You made a statement that these are only of Fresnel lens type, which basically means you are saying that these are geometrically optics based, which is not true, because we are dealing, just a moment, if we are dealing with the high numerical apertures, and you are yourself saying that this is diffraction limited, then within the broad category of DOE, these are diffractive optical elements.
This is not based on diffraction. That's the main difference, sir. And also it can lead to...
This is a phase structure. So phase structure also diffracts light, and you cannot wish away diffraction. And if you see the photographs, the very good lenses of this type give you airy pattern.
That is true.
Airy pattern itself means that these are working as diffractive optical elements. I have followed this subject very closely.
Only thing is that it is possible to incorporate other aspects so that you can beat diffraction in the future. It is not done yet, but there are ideas to beat diffraction in this.
No, but in a high quality system, diffraction cannot be wished away.
That's right. So you can incorporate negative lens approaches within this so that you can meet diffraction.
Not necessarily negative.
No, yeah, maybe other methods, but it is possible. There are ideas where people have shown that you may be able to beat diffraction using these meta lens approaches.
Anyway, there are
currently simply the method which I followed, you cannot beat diffraction because you are still having a numerical aperture limit and also the size and the focal length. So the approach which I mentioned, it will not beat diffraction at all. Only the size will be smaller in nano dimension, thickness. And also you can have multiple elements one by one, integrate multiple elements along the length, so that one lens can achieve like a lens spectrometer, it can behave like the spectrometer also under that. So all can be combined into one. It is possible.
So that is all right. That is being done.
Yeah.
But I still maintain that if these have to be of high quality, diffraction is present.
Absolutely, it is limited by diffraction now.
Its effect can be minimized.
Yeah.
But it is present, and that means these are DOE.
No, I don't call it their DOE because the focusing is not done through diffraction.
But there are many papers in which diffraction effects have been very extensively studied in these kind of...
That's because of the repetition which will lead to diffraction also. But the focusing is not done through diffraction. That's what I meant. In the diffraction optical element, it's the diffraction equation which governs the redirection of the light. Here it is not governed by the diffraction. Redirection of light is not governed by the diffraction equation.
That is okay.
That's why I don't call it diffraction optical element, because that
means phase is only changing the direction of the...
That's correct. That's right.
So that means these cannot be of very good quality. Anyway, we can discuss this later.
Thank you, sir.
Kedar, you have a question?
Yeah. So the question is, with the traditional optics, the phase is
associated with optical path difference through the glass. So
That's right.
how is the phase interpreted here? It is just the density of these nanopillars, or?
No, it's basically the phase can be changed. Here, it's the confinement of light in the nanopillar, and it's like a waveguide. So the resultant effective index of that waveguide defines the effective phase.
Yeah, so it's still optical path length to some extent, but
to some extent, but that's only nanopillar idea. There are many other ideas which do not work on this.
Right.
So the nanopillar idea works like that.
Right.
Okay. Any other? Okay, I think.
I just one question, Anurag.
Yeah. Yeah.
What is the fill factor of the nanopillars in the structure?
Okay, so nanopillar currently it's around something like 50% of the area. It depends. Okay, so you go all the way up to 100% from around 40% to 100%, because as you see, each unit cell itself 200 nanometer. Each unit cell is 200 nanometer, and so the size of the nanopillar is varied from 100 to 200 nanometer in this study right now.
So the space between the nanopillars that will contribute to effects on your image.
That's correct. That's correct. So these have to be separately. That's correct.
Yeah. Okay. Okay. Thank you.
Joby, are you planning to generate all these things in IIT?
Right now, we can do that in E-beam lithography, but at present, I am going to make this in NIST with Dr. Amit Agarwal.
But from NRF, we can make, right?
We can make, yeah, we can make. But,
I have to make some of the polarization elements.
Yeah.
I will send you.
Right. Thank you.
Okay. I think we can continue now. Now, Joby, you can take over and run the rest of the session.
Thank you, sir. So our next speaker is Dr. Arvind Kumar, who has been my senior during the PhD time, and he is still with us after his retirement. I will hand over to Dr. Arvind Kumar. Thank you.
आ रहा है आपका आ रहा है ये किसका है हेलो
Yeah.
Okay, आ गया
Can hear you. Your screen is
Yes. Please speak. Your slide is visible, Arvind.
Sorry, my talk will not be on very topic specific or something. I will talk in general. Because I joined here in 1982 and I was here on the post up to 2012. So before joining my here, I did some work in rural development here. I did some work on solar biogas or something. After that, I joined this lab. Hello?
Yeah.
Are you hearing?
Yeah, please go ahead.
Okay. I joined this lab in 1982 to look after the MTech applied optics lab. With this Professor Sir was the coordinator. So I spent around 4 years in that lab. After that, spending 4 years, then interest and optics developed, and then I have decided to do work on optics. So I started work on using speckle technique for the small measurements, in plane, out of plane measurement, vibration measurements, and other techniques, and did my research. I got my thesis submitted, and I submitted my thesis in 1994 and got a PhD in 1995. After that, I continued my research on related fields and helped several research scholars in their research work for PhD degree on precision engineering measurement, biophasing photonics crystal as the recording medium, as well as work on engineering measurement by utilizing the beam fan generated by utilizing photoreflective crystals as the recording medium. So that I did some work with some students on optical correlators also, and the correlator technique has been used for the measurement of small displacement, and then started one on optical security. So we have published so many papers on optical securities also. So Still I'm doing work here on a project in shadowgraphy funded by DRDO. After my retirement, I got this opportunity to work here in the physics department, for which Professor Javi Joseph is the PI, and Professor Sanjil Kumaran, Dr. Kehar Singh, the co-PI. So this was about all my journey here. I'd like to show some research papers, and these are a few papers which I published here. So, okay, thank you. I presented some.
Okay. Thank you, Dr. Arvind Kumar. Anybody has any question?
अरविंद जी बहुत दिन हो गए आपकी. I wish I could see you there on the video. कैमरा तो ऑन कर लीजिए. It's been such a long time that I haven't seen your.
Yeah, thank you, Arvind जी. आपका वीडियो नहीं आया Arvind जी.
अच्छा वीडियो नहीं आया.
हाँ, everybody wants to see you after a long time.
Yeah.
Yeah, there is.
Yeah, yes, it's there.
Now it has come.
We can see you.
Still I'm in the lab.
He is still in the lab. He does not want to leave IIT at all. He is still in the lab. Thank you, Arvind ji. So let me move to Dr. Sanjay Kumar, and who is actually the brother of Dr. Arvind Kumar. And he, after the PhD with Professor Kehar Singh, and he has been in industry with developing holograms quite a long time, and he made laboratory and made all the holographic embossing work done. And after which now he is teaching in Delhi College, and I invite Dr. Sanjay Kumar to start his presentation.
Okay, thank you, Dr. Javi. First of all, I want to wish Kehar Singh sir happy birthday, sir. Though we are celebrating 80th birthday, but you look like 18 years of old. So congratulations, sir, for your health. All should get similar health. I wish.
You can share your slide, Sanjay.
Yes. Professor Javi, when I share my screen, sometimes it goes off. Then I will join from other device.
Okay.
So if it happens, then you can allow Dr. Kamal for that, then I will do. Okay.
Okay.
But
please
sometimes.
Okay.
मैंने शेयर किया था. शेयर हो गया क्या? Can you see my screen?
Not yet. Can you press the share screen button, share content button?
I have pressed that.
After pressing, then either you go to screen so that you will see your computer screen, then you can open it, or you select the window of presentation.
Now you are not getting the screen?
Not yet.
No.
Yeah, no, not yet, no.
It's not getting shared.
Yes, it is coming.
It is coming. Okay,
Yeah,
thank you.
it will take some. I think it will come up, but I think it's on the way.
No. इसका चार्जर लैप का ये लीजिए मेरा लीजिए.
Yeah, we can see your computer screen. You can open your PowerPoint presentation, then it will come.
I have opened it.
You press that, then that will come. Press that PowerPoint slide.
मैं तो नहीं देख सकता हूँ. It is visible on my screen. Can you see it?
We see your computer screen of Microsoft Teams.
You have to open.
You can minimize that probably, then it may come.
Maybe slow. Because on my screen.
You can go to, please go to next slide. Let's see. Or you can.
Perhaps he has pressed the button to share one particular application, and he has shared the Microsoft Teams as one of the share. So he has unshare that and.
Yeah, please unshare that once more. Please do unshare button. Press that share button once more, so it will unshare.
Okay.
Then do that again and
choose the PowerPoint, not
choose the PowerPoint.
Is it visible now?
No.
No. Then I will try, Professor Joby. You can ask Kamal. In the meantime, some problem is there.
Okay. I think I will go to Kamal Sujit, who has been my junior, and after PhD now she is in Bangalore and with her family, and currently I will share the slide, which just one slide on which she will be speaking about. I will share that particular slide. Sorry.
First of all, very, very happy birthday to you, Professor Kehar Singh, sir. You've been my mentor and you've been guide in my whole journey of IIT Delhi of learning whatever I know of photonics. Thank you so much for that. And it's heartening to see you in such a wonderful state of health. And we wish you a very, very long life and more of good health and more of photonics to you, sir.
So I hope you can see the slide now.
Yeah. Am I audible?
Yes.
Okay. And a big congratulations to the whole fraternity out here. It's a real celebration to come and be in the midst of all the dignitaries of the senior teachers and my colleagues and the juniors who are here. This couldn't have been a better way of celebrating sir's birthday out here. And so thanks a lot to Professor Anurag Sharma, Joby Joseph, Naveen Nishchal, and Renu John for organizing this event. And it's a big hallmark of anything that we see that Center for Research in Optics and Photonics is taking a shape, and that is a kind of a landmark achievement for the department, and especially for the Photonics lab for this one, the whole department, I would rather say. And I feel very proud, though I'm not directly related to the work, but there's always an itch, how do I connect what I have learned into whatever I do it in my life. So the topic that I chose and I gave to Joby was science, women, and sustainability. Science is my thought process, woman I am, and sustainability is the way of life. Not just for me, for the families, for the communities, for the world. Because today we are just standing at a climate emergency. And sustainability, what it means is nothing but innovation and adaptability. As a woman, as a science student, I've tried my best to be as innovative and adaptable, whether it was my profession or it was my family, to make sure that I kept moving from one pillar to another pillar and do justice to what the learning I had and for the work that I was doing. So my journey started, my destiny brought me to Delhi in 1989 for MTech in Applied Optics. And I happened to do my thesis under and project work under Professor Kehar Singh. And I was so in awe with the subject that I chose to do the PhD also under him, continuing the work that I had done. Joby, you have been my half guide. You actually showed me that the first lab, that entering into that lab and seeing the lasers for the first time and knowing what holography was, that was a kind of a new world to me that I opened up. And with Professor Kehar Singh's guidance in all form, the way you molded, that you polished, you educated, it helped me come to a point where, of course, there are two feathers in my cap that I still feel proud about, is that I managed to do a best paper presentation during my tenure in physics in PhD. And second was that I broke the records and I became the first woman to complete PhD under you. So that is on a lighter note. Now, having learned about photonics and going towards being married to an architect, the journey was all about becoming a building physicist. First of all, I saw no connection. I thought I'm lost. But the more I was learning about the profession, slowly I learned that everything about the building is physics. Whether you're talking about daylighting, you're talking about artificial lighting, it's optics. You're talking about thermal comfort, you're talking about air conditioning, HVAC units. It is all about heat transfers, about computational fluid dynamics, you talk about structures. It is all about stress, strain, Young modulus of elasticity, thermal expansion coefficients that we see it in the structures. So every aspect that we pick it up, first of all, it is nothing but the physics of the building. And I felt that I can bring my expertise into it. And at that particular time, the green building was taking shape. As Professor Dr. Kanpal was also mentioning about human-centric lighting. See, everything is all about wellness. We all spend about 90% of our time inside the buildings. The buildings affect us. At the end of it, it is the wellness about it. So the wellness basically is a very holistic one. How does it come into action is that whether it is a human-centric lighting, whether it is a thermal control that we are doing into the buildings, or we are living into the painted structures which are emanating volatile organic compounds, which are affecting our breathing systems and bringing illness to us. At the end of it, it's all about wellness. The science and the physics of everything and the chemistry of everything is working in the biology of the system. And then it is telling us that everything needs to be balanced, needs to be sustainable the way we are doing it. And in this journey, I worked very closely with Confederation of Indian Industry and worked with Indian Green Building Council. I also worked with US Green Building Council and I became an accredited professional with them. And I was working in the benchmarking of the buildings in being whether they are green buildings or the healthy buildings and the wellness factor is there or not. And that's how my career path was going into it. Also, I worked with affordable housing, how to bring the material aspects of it, in which there are two aspects in sustainability that we talk about primarily. One being the environmental, the other one being the affordability. So when a designer is building a building, is it only building it in terms of the design that he wants to do? Or at the end of it, what is the life cycle impact of it's going to be on the wellness of the people and also on the wellness of the building, how long it is going to survive. And in the time of the things when the fire happens, the flooding happens, when you have problems of electric breakdown, how resilient the buildings are. So these things have now become a new topic of discussion all over the world. In US, this is now in UK, they have taken up now the carbon neutral agenda. So when we are doing the buildings, they are having a kind of a drastic effect. So the poster that you see in front of you, the climate targets, the whole world has now committed towards being carbon neutral. Building industry is responsible for almost 40% of the greenhouse gas emissions. How can we optimize those ones? So this is becoming a kind of a transport is one big area which is responsible for the GHG emissions and for the climate change, and the building industry is hugely responsible for it. And as being a building, a green buildings person or a building physicist, I bring my knowledge into this domain and see that how we can optimize energy performance of the building, indoor air qualities, in terms of your water management, waste management, and how can we develop net zero campuses so that the portfolio of the buildings that any company or any institute can have is a net zero campus. My recent work or interest is now, the right bottom slide that you see is about satellite imaging. So I'm working very closely now with the University of Washington, where they have a program called Carbon Leadership Forum. And I have associated with them and brought their first chapter in India and second in Asia, where we are taking the cities towards a net zero neutral agenda. How to go about it? The satellite imaging is playing a very, very big role. And I'm excited about this project because this is exactly like where my knowledge domain in photonics will come into picture, that how using the satellite imaging, we can monitor building defects, condition monitoring can be done, even construction management can be done, project management can be done, heat island effect, which is like a huge problem for this all climate disasters that are having. How can that be monitored? And the maintenance cost optimization can be done. So that's been my journey as a woman, coming from a science background, using for whatever I've learned, going towards a world, helping world in my profession to sustainability. Thank you so much with that, and thanks for patient hearing to all. I also want to mention, Ghatak sir has mentioned, is there any company which does human-centric lighting? So if he's listening to me, there is one company by the name of Energy Focus. They do LED lightings, which basically changes your light pattern, and they have a control on the thermal temperature inside the lamp, which basically emanates light into a different Kelvin temperature, and it gives you different color lighting, and it follows your sun path. So these are some very intelligent innovations that are happening, sir. Thank you.
Thank you. Thank you, Kapil.
Very good.
Thank you. Any questions from anybody?
Yes, sir. This is Sanjay Misra, sir.
Yes, Sanjay.
I want to ask, Madam was talking about the wellness inside the house. I want to just ask that, is there any way to whatever the electromagnetic radiations nowadays is inside the house where we are living, so it is getting controlled by some way?
Yes, so I am very passionate about traditional knowledge that India brings, whether it is in terms of Vastu or it is about traditional materials and technology that we are having. There is a person called Dr. H.C. Malik, who has actually worked with IIT Delhi a long time back, and he is working on using cow dung to use plaster and I am yet to go and meet him. I've been postponing my visit to him because of the COVID situation. But if you use that as a plaster, so let me just explain this a little bit more. See, when we look at the structure of the building, the 80% of your greenhouse emissions come from cement and from steel. If we do innovations in these two parameters, we can reduce down the greenhouse gas emissions to a large extent. So he has come up with a plaster which is used by something Chuna Bhatti. If you remember, I'm sure Kehar Singh sir, you will remember that every village used to have a Chuna Bhatti, and it was used as a kind of a plastering material into our buildings, and it was a very good thermally insulating material. We have forgotten that knowledge. So he is now mixing that tuna with the cow dung, and he has come up with a plastering mechanism which does not need curing at all. So it is not just that you are not using cement, but you are also saving on water. Water is our next oil. So, and this particular material is capable of insulating your electromagnetic radiation also, is what he claims, and I'm also interested in exploring that. Thank you.
Okay, thank you, madam.
Hello, good afternoon, Joby sir. This is Madhusudan Joshi.
Yes,
yeah, just wanted to make a small comment and add to what Dr. Sujit has just said, and to answer Mr. Mishra's question. You see, all the devices, if you are talking about all the devices we are using in households nowadays, where we have a lot of electromagnetic radiation which is suspected, But just to add to your query, sir, that all these devices are normally being tested for safer limits of electromagnetic compatibility, and all these devices are completely safe to be used in households. So all the devices like Wi-Fi LANs or Bluetooth devices or whatever you use inside the houses, whatever gadgets you use are all being tested and validated for their electromagnetic limits, and thus safe for use. Thank you so much.
I think Mr. Sanjay's concern is not from the phones, but also from the transmission towers, which is very huge.
That's also
no,
also
madam,
very well regulated by DOT.
I think
I
let's
have the
discuss those things
I
later.
have the cross argument. I have a cross argument over this. Basically, for one device is calibrated and it is basically safe for that. But nowadays, because lot of online things and kids are doing lot of online things at the home, when there is a density of devices is increasing inside the house, what is the impact of that on the kids' health? That is my point.
Professor Jyoti, if time permits, I'd
just one quick question, not a long one. Yeah, please. Then we can go to the next.
Dr. Kanwal, for a very long time, I've been looking for some solution to bring sunlight to basement or places like that, and I came across one French company who's been offering an optic tube kind of thing. But can we have some other technology where we can directly use some kind of optical fibers with funnel kind of thing attached at one end and something of the same sort at the other end? Have you come across
Dr. D.S. Mehta, our Professor D.S. Mehta has been working on this topic for some time. I think you should have a discussion with him. Maybe he has been working. I do not know how successful it has been, but you should get in touch with him.
Yes,
sir, one quick comment to Dr. Ganotra, that there is a device available with 3M in Bangalore, which is like a tube. It can bring the entire sunlight to your room, like as if there is a source on the top of the. So I've seen that physically in 3M Bangalore.
Wow. Okay, thank you.
Okay, thank you very much.
So
I think
we can move on.
Yeah, let's move on. And Dr. Sanjay, are you available?
Yes, I am here. I start my presentation. In the meantime, screen will also come.
Yeah.
So actually, I joined Applied Optics Lab in 1985 when I came to Delhi after completing my MSc, and when I went to meet Professor Singh. So I have collected a lot of courage before entering his room, because Dr. Arvind Kumar told me about his hard working and so many things. And then I worked at the rate of rupees 30 per working day for 5 months. And then I got interest in holography, and then I shown my interest to sir that I am interested in holography. I got in a project, holographic display, is sponsored by the DST, and since then I have worked for a long time in the holographic industry also. I have done PhD also. So there, Professor Joby, can you see my screen now?
Yes, it's working fine. Yeah.
Okay. So then I started my work on bleach phase holograms, but before that I have made a large number of display holograms in IIT Delhi. So it was the time when the experimental work was done, say at the last of 86 or like that, we started recording a large number of holograms for display purposes for that project. And then I started my PhD in 87. My topic of PhD was bleach phase holograms, diffraction efficiency, scattering and stability. And there I have optimized one bleach for the conventional bleaches by the name of conventional bleaches, and then one bleach by the name of reversal bleaches by using the photographic material. Then I published that at that time 16 publications before the submission of my thesis, and then I continued some work, and total 20 publications and 14 research papers in conferences, and 4 times DU have called me as a resource person. In addition to that work, I have worked 15 years, 4 months in industry also. Here I have installed 4 holographic labs and all 4 are in the working position. But now the main work in the industry comes as a security holograms. We know about the optical security. A large number of topics are there in optical security, and those are very important, comparable or more than that of electronic security. So optical security, we know the benefit that we can do parallel processing like that. So, but I selected the holography field. So security hologram. Security holograms are the holograms used to stop the duplicacy in the market for the recognition of authentic document or like that. So in that security holograms, we have given different, not we, the all over world scientists have given different name. The first one is 2D 3D hologram. Actually what we use here, we use the holographic recording process and we play with the slits actually. We make a rainbow hologram. For that we have to use the slit to make the rainbow hologram, and we play with that slit actually. So we don't use single slit as a whole aperture. We divide slits in different parts, and then we select the object information. For one part, one object information. For second part, the second part of the object like that. So we call that 2D 3D hologram. It means we are recording the 2D hologram and then we are moving some parts and the recording another part of the image, and by that we give depth. So we call that 2D 3D holograms. And in the same way, we use type of holograms. So in the types of hologram, dot matrix hologram is there. In dot matrix, what do we do? Actually the technology is the same, but utilization is different. So in dot matrix, we take 2 beams in the form of dot. They meet at one place, and at that place we put the photoresist, and then we move the photoresist. So it is a kind of angular position which decides the security levels. We record in different, say one frame, one security level, then second frame, second security level. So we can add say more than 15 security levels in the hologram, and depending on the addition of the levels, the cost and its utilization increases. The holograms are used on Visa card, on bank notes also, and there are wide applications of these security holograms. Then one kind of hologram is a flip hologram. There we record hologram at 2 different angles only. So when one is visible, other will not be. When we will change the reconstruction angle, the other image will come. So by using that, we can record say 2-3 images on the same photoresist plate. Then electron beam lithography. By using the electron beam lithography technique also, you can do the engraving in the photoresist, and then you can get the required information of security. So possible features in the holograms, because this electron beam gives the best resolution available. So we record different types of images. We call that Gulache pattern, concealed images, kinetic images. But the main thing is, the main principle of recording is the same. People use in different way, and we call that by the name of different technology. So for that purpose, I got training for 1 month from US company Chromogem. Then in the second phase, I got training for 5 weeks from Hologram Industries France, and then one more training was given by the Chinese scientists, and all the 3 were using in different ways. Then I was in Holistic India Limited. I combined all the 3 technologies and made some new products in Holistic India Limited, and due to that, Holistic India Limited was the biggest company in India for making the embodied holograms. So similarly, if you want to see some code by laser viewable code you want to give in the hologram, you can give, and you can use computer synthesized to 3D hologram also. So there are various steps for increasing your security. But as a principle, holographic and reconstruction principle is utilized. The same principle is utilized in the industry, and embossing, for embossing purpose, you need to make to transfer the photoresist image onto the nickel, and then embossing purpose you can make multiple copies like that. So in
Dr.
the
Sanjay,
market,
please finish in 1 minute.
Yes, sure. So in the market, main thing is you have to use holographic technology in different layers. You have to add the security, and the most effective hologram is the true color images. When you record on the same photographic image, we can have more than 40-50 exposures also. So you can increase your security by manipulating the slits like that. So rainbow technology is used. Slit, you have to play with the slit, and then you have to do the work. So security, you can increase as much as possible security level. So this is all about the security holograms, and the cost for getting this is, say, 40 lakh rupees people charge for giving this technical know-how. In India, 2-3 companies have purchased it, and what I have mixed all the 3 technologies and used for one private company. Then I left and I joined the Acharya Naindev College, Delhi University. So that's all about my talk. Thank you, Professor Jovi. Thank you very much for allowing me. Thank you.
Thank you. Thank you, Dr. Sanjay. And any question, 1 or 2, please?
You have just a comment.
Yes, sir.
Had some consultancy projects from state governments, quite a few of them, and they use these, their excise departments use these in liquor bottles. So I must acknowledge Sanjay Kumar's help in making me understand some of the very intricate points, some intricacies of making and testing these security holograms. That's just a comment I like to make.
Thank you, sir.
Thank you.
Yeah, and Dr. Ashok Bhatia, you have any question? You have raised your hand. Your voice is muted. Can you unmute yourself? No sound, sir. No sound is not coming.
He can contact me personally.
Yeah. I think you may contact him. Sorry that your sound is not coming. Thank you very much. And we'll go to the next speaker. That is Dr. G. Unnikrishnan, and from IRD Dehradun. And as a matter of fact, I am proud, and in fact, Professor Kehar Singh too, that the highest number of citations from our group is from the work by Dr. G. Unnikrishnan on encryption, more than 1,000 citations. And it's commendable. Thank you, Unnikrishnan. So can you hear? And I don't see you, but Unni?
He was there earlier.
Yeah, he's there. I see.
Yeah, I'm here, sir.
Okay. Can you please share your slide?
I'm just doing that. Yeah.
Okay, thank you.
Is it visible?
Yes.
Am I audible?
Yeah.
Yeah. So at the outset, I wish Professor Kehar Singh a very happy birthday. Wishing him many more years filled with happiness, joy, and good health. The brief talk today, the outline is that I'll discuss specifically some challenges in realizing wide field of view, high resolution imaging systems. And if time permits, I'll talk a bit about my research at IIT Delhi. So when we talk about long distance imaging, there are three parameters which is of most interest. One is the field of view, other is the spatial resolution, and the range. So surveillance systems, which has many applications, including defense, there's a lot of interest in building systems with higher and higher resolutions over wide field of view. And of course for longer and longer ranges. So the question we address in today's talk is, can conventional camera architectures achieve all these requirements of field of view, resolution, range? The conventional way to build such systems would be to increase the number of detector pixels or use large format detectors, and even for larger detector pixels, you tie different detectors and create a large detector array. But the overall performance of the whole imaging system would still depend on the performance of the optics. So, what would be the optics that would go into such a system? So, let us look a little bit more closely at this field of view and resolution. For optimal camera performance, that is for a maximum information flow between the optics and the detector, one would require the IFOV of the detector as determined by the detector pixel size and the focal length of the optics should match the angular resolution of the optics. So this is one of the basic requirements while designing any imaging system. Now, longer ranges would mean the IFOV has to be smaller, and to meet the requirement of that the IFOV match with optical angular resolution of optics, one needs to scale the optics. So you need to go for higher and higher scale optics. Now, for some researchers like Brady and Hagen in a paper, they have studied what is the space value product. Space value product actually characterizes information carrying capacity of the imaging system as defined as a number of resolvable points. To achieve a 1 gigapixel resolution, what would be the for a different FOVs? What would be the lens aperture that would be theoretically needed? So this calculation was made, and what they found was that for a 30-degree field of view, which is a good curve, what would require an aperture of something like close to 8 mm to achieve a 1 gigapixel image. But it actually would build such a system with the effective aperture of say 8 mm. The performance is far less than what is given by the theoretical limits. So the question is, why is this happening? And the answer was given in a paper by Roman in way back in 1989, where he pointed out that as the optics is scaled up, there is no corresponding increase in the space value product as one would expect. due to aberrations. What actually happens is that as a state of the fractional size remains the same, but the aberration bus size increases, and thereby the space where the product is found actually scale up as one would expect. So now, so the crucial thing is how to balance apertures for larger and larger apertures, so that the conventional optical conventional way is to add more surfaces to balance aberrations, but this would increase the complexity at the cost of my performance, and there's a limit to actually do this. So. But a solution was an elegant solution to this problem was proposed by Brady and Hagen in 2009. What they actually did was they decoupled the need for achieving the required resolution and the controlling the aberrations by proposing an architecture where the optical field is processed using optics at different scales. So they call it a multi-scale architecture, and smaller aperture optics is used for controlling the aberration, as it is much easier to control aberrations in smaller apertures, and a larger aperture lens means a complete solution. Based on this principle, Aware 2 camera was built by the DARPA program, which was achieved with that by the university, and they successfully built a 1 gigapixel camera, 120 degree field of view, and this was what the details of this camera was published. So now at IRE we are trying to use similar concepts to build the high resolution wide field of view systems for IR. The challenges in IR is, in addition to what that discussed now, are quite different, and we are trying to we hope to successfully build a.
Please finish in 1 minute.
Yeah, successfully build such a system in the next 2 years. I'd like to talk a bit about my research, and my topics. The topic was optical security, and we actually show here is an experiment. This was one of my first papers, and this was an experiment to actually perform encryption decryption operation completely in the optical domain by generating a conjugate of encrypted stories with this combination of crystal. So it's quite a tough experiment, and unfortunately, I had a lot of fun from Derby sir, who had worked on that time, and I'm extremely thankful for that. I would acknowledge the support and guidance of Kehar Singh during the entire career, and all the other members of Professor Singh's lab who were with me during these 2 years. I thank each one of them. Thank you very much.
Thank you. Thank you, Oni. And any questions, please? You can unshare the screen. So that was the work which has around 1,200 citations, which Unni mentioned. Any comments? Okay, so in that case, we can finish this session. We will go to session number 4. Andreas Sharma sir?
Yeah. Okay, thank you, Dr. So we are still half an hour late, so you have done quite well with time, whatever adjustments happen. Okay, so now we again come back to some of the colleagues and former indirect students, I would say. We are mostly from the Fire Optics group who are going to speak in this particular session, and they have been very closely associated with Professor Singh in some way or the other, including me. I'll come to my talk is at the end. So I invite Professor Arun Kumar.
Okay. Thank you. First of all, there are a lot of noise. Somebody.
Yeah.
Yes. So,
Sir, I think you have to mute everybody. Then Arun Kumar sir should unmute himself.
okay. Okay. So to share this, I go.
Yeah, Arun. Arun, unmute yourself.
Okay. Can you hear me now?
Yeah.
Acha, to share the, I get to share Microsoft PowerPoint, right? Can you see my slides?
Yeah, they're coming, I think. Yeah, okay, yes.
And how do I go to the presentation mode?
There only at the bottom you have that.
Okay, okay, right.
Yeah.
So this is fine now?
Yeah.
Okay.
It is, no, it is coming. It is not yet presentation mode. But it's okay. You can go like, sometimes it doesn't work.
No, on my screen, it is a presentation mode.
Okay, so it's okay. You can go ahead.
First of all, I would like to wish Professor Kehar Singh a happy birthday and birth decade, in fact, right? So, and then next, I would like to thank the organizing team, Professor Anurag Sharma, Joby Joseph, and Naveen Nishal, Renu John, for giving me this opportunity. And without losing any time, let me start. The topic of my talk is metal-clad optical waveguides for sensing applications. Now, why metal-clad waveguides are okay. So the outline is I will give a little bit introduction, then I will discuss metal upper-clad waveguides. Then that is when the
you have not gone to the next slide. Actually, there is, you click on the left panel.
Left panel.
Yeah.
Okay. No, moment. So how should I go to the next slide?
Yeah, that's what I'm saying. You click on the left panel first.
No, he is already in the presentation mode. So you right click and put it back on the normal show.
Okay.
So what?
उसको कैसे?
Go slide by slide.
अच्छा. So like this? Okay. Now can you see the outline?
Okay. Yes.
Okay. So introduction, and then I will discuss metal upper clad waveguides where the metal layer is deposited on top of the waveguide, then metal underclad waveguides, and I will summarize it, right? So then can you see the next slide now? Have you?
Yes, please.
Go ahead.
Okay, fine. So why the metal-clad waveguides are unique? They have a unique feature because of the fact that even a single dielectric metal surface that can guide an electromagnetic wave, and this electromagnetic wave is known as surface plasmon mode. And this has a very special characteristic that the field in the metal that is has a confinement which is the sub-wavelength confinement. So it basically gives the diffraction limit. So that gives a unique feature to such waveguides. So on this slide, for example, I have given a small calculation that if you consider a single dielectric metal interface, then the electric field variation, modulus of electric field variation would look like this. But if you calculate the characteristic, this effective index of this surface plasmon mode, that is given by this expression, under root epsilon r. Epsilon r is the real part of the dielectric constant of metal, and epsilon 1 is the dielectric constant of the dielectric. So what you can show that because of this minus sign, effective index is always greater than the refractive index of the dielectric medium. And if you use this and put it in the, you find out the field penetration in the metal. See, field in the metal would be decaying as exponential minus gamma x, where gamma is given by this expression. So this calculation is quite straightforward, and you can see that the field confinement is of the order of lambda by 28. So this is a unique feature of metal-clad waveguide because the field in the metal is very
very much confined near the interface. So any change in the dielectric or medium near the metal surface, that can be detected. So as a result, such waveguides or such structures, they are very they are being used for biosensors, where you have so very tiny samples to be detected. Now this is just one dielectric metal interface, but if you deposit a metal layer on top of a waveguide or underneath it, you will have a thin metal film, so which will consist two metal dielectric interfaces, and this metal dielectric, this metal strip, that would support the modes like this. So the first picture shows the single metal dielectric interface, and the second picture shows that you have a metal film surrounded by two dielectrics on both the sides, and as a result, like in a directional coupler, the surface plasmon mode supported by the upper surface and lower surface, they would combine, interact with each other, and as a result you will get two modes, one in phase combination and one out of phase combination. And for example, this is the in phase combination and this is out of phase combination, and this we call as symmetric supermode and or symmetric anti-symmetric supermode. And by the way, if this symmetric combination, this is known as long range surface plasmon mode, because the loss of this mode is comparatively low as compared to that of anti-symmetric supermode. And on the other hand, if I would have a dielectric film in between and surrounded by metal, then the field would look like this. So what happens when we deposit a metal film on top of a waveguide, or then we basically couple energy to either one of these modes, symmetric supermode or anti or long range or short range surface plasmon mode. So let me show you that this, using this fact, surface plasmon mode, in bulk optics, two geometries are very popular, Crestman configuration and Otto configuration, which are used to sense biological samples or refractive indices, and this works like this. So you will have a prism, although most of you are familiar with this. So this looks like this. So you have a prism of high refractive index, and in one of the geometry, Crestman geometry, we immediately have a metal film, and then you have analyte. So if you if you make a light beam incident at the base of the prism, then at angles when you have a total internal reflection, then the surface is supported by the prism metal interface that couples to the surface plasmon mode supported by metal analyte interface, and the output beam comes out at a if you do, I mean, and that how much energy would be coupled, that would be basically decided by the this phase matching condition. When this phase matching condition is satisfied, that the propagation constant of the surface wave at the bottom of the prism, that matches exactly with the propagation constant of the surface plasmon mode, then energy would couple to the surface plasmon mode. And because surface plasmon modes are highly lossy, so in the output which is detected here, you will get a dip. So in this picture, if you plot a angle of incidence as a function of output intensity at a certain angle, you will get minimum intensity. That is the angle where the energy is coupled to the surface plasmon mode. So this experiment can be done either with respect to by changing the wavelength or by changing the angle of incidence, because basically this phase matching condition is a function of angle of incidence as well as wavelength of light. So both the possibilities are there, but in bulk optics generally it is the angle of incidence which is detected. There is another geometry, auto configuration, and there you have another dielectric at the base of the prism, then a metal film, and then an analyte. And now you, in principle, you can couple energy to the symmetric as well as anti-symmetric surface plasmon mode supported by this metal film. But generally, it can be shown that it is the anti-symmetric mode which is to be coupled, because because the effective indices of the two modes are like that. So
Now what I will discuss that these geometries, they have people studied in the waveguide geometry also. For example, the Scratchman geometry can be realized in optical fibers. So for example, you can take a multimode fiber and you can directly deposit the metal on the core, and this is possible because we have what is known as plastic clad silica core fiber available in the market. You just remove the plastic cladding little bit and directly deposit metal on top of it, and then you put analyte here. So this is the Scratchman geometry in optical fiber configuration. So Professor B.D. Gupta in our group, he has made a very extensive study of such a structure. And another auto configuration you can achieve either by leaving some cladding on top of the core, or a very popular geometry is what is known as polished half block. So you have a single mode fiber, and on one side you side polish it and then put a metal layer on top of it and then analyze. So this is the auto configuration, and a large number of work has been reported in this direction on biosensor. Particularly Homola, he has also written a book on this, and he has reported a lot of work. But optical waveguide configuration is becoming much popular now, because in optical waveguide configuration you have the flexibility of selecting materials, etc., and dimensions very easily. In optical fibers, whatever fibers are available, you can use them only. But in this optical waveguide geometry, because you can deposit layer by layer material, so you can select dimensions. You can. So what I will discuss this waveguide geometry basically, right? And now most of the work reported on metal clad waveguides use the surface plasmon modes, which are TM in nature, but they are highly lossy. What I will discuss the metal underclad waveguides and using TE modes instead of. We have done some work in the recent past, and basically I would be discussing that. And before coming to that work, so let me first tell you that what is the main characteristic of such a waveguide. If you consider metal undercladding, then you can show that let me consider, suppose the two modes are supported by this waveguide, TE0 and TE1. So in this figure I have shown that what is the effective indices of the two modes in metal underclad waveguide.
2-3 minutes more only now.
Okay. So without going in detail in these slides, let me tell you the two things we observe. Effective indices of both the modes decrease, and the fractional modal power in the cover region increases very significantly. Second, the enhancement of the fractional modal power due to metal undercladding is much larger for TE1 mode as compared to TE0 mode. So what we have done, we have exploited these two features to propose various sensing structures, and some of them I will discuss here, right? So we have reported modal interferometers. And let me directly come to the structures we have proposed. So we have proposed a refractive index sensor. So you have this is the dielectric waveguide, and underneath you have a metal surface. This is the cross-sectional view, the two modes supported by the two mode region. And so this works as a modal interferometer. You have a single mode waveguide, then it excites two modes of the waveguide. Output basically gives you the interference pattern between the two modes. And using this typical this spectrum, transmission spectrum. So what I would like to highlight that one can get sensitivity as high as 75 micron to 110 micron per refractive index unit. If you convert in the absolute units, it would be of the order of 10 to the power minus 6 or minus 7 refractive index resolution. Then we have, the temperature sensor we have proposed. In that case, we have covered the dielectric region by PDMS, which have a very high thermal expansion coefficient, thermo-optic coefficient. So, and very high temperature sensitivity we have reported.
Then we have also shown that because exploited this high evanescent field in the top medium, and have shown that if you use a Bragg grating in a waveguide, then the sensitivity can be enhanced tremendously. For example, this curve, this spectrum shows the out reflected spectrum of a Bragg grating when there is no metal undercladding, and this shows the spectrum for different refractive indices, outside refractive indices, when there is a metal undercladding. Just to show you the difference, this is the sensitivity and figure of reported in normal ridge waveguides, and these are the sensitivities of metal underclad waveguides. So you can see, as well as figure of merit, a order of magnitude increase. And finally, I would show another structure where a long period grating is used. So you have a single mode waveguide at the input, and output in between you have two mode waveguide. And so single mode waveguide, the fundamental mode excites, basically dimensions are selected in such a way, most of the power is coupled to the fundamental mode of the two mode waveguide, and when the grating period is selected in such a way, the coupling takes place from fundamental mode to that appropriate higher order mode, and then you get again the output. So in this case also, without going that why we have selected TE20 mode to couple, let me tell you the final result. The sensitivity is somewhere between 38 to 100 micron per refractive index. So finally, I will conclude that what we have shown in the last few years, that metal-clad optical waveguides, of course, are discussing this lecture. It is shown that metal undercladding greatly enhances the evanescent field in the ambient medium and help in realizing this dispersion turning point. I have not discussed because shortage of time, but this metal undercladding also helps in realizing the dispersion turning point in the two mode region, and which can further increase this sensitivity. And we have proposed metal underclad waveguide structure based on modal interference, Bragg grating, long period grating, having ultra high refractive index and temperature sensitivities and compactness. So I would like to thank you and acknowledge my two students, Ranjit Dwivedi and Navaran Shah, and finally thank you for your patience. If there is any question.
Thank you. Yeah. Any questions? Arun, you can unshare now.
Okay, unshare ke liye I will go there.
Same button.
Same button. Right.
That arrow.
Scope sharing, right. Yeah.
Any questions? Any comments? Okay. If not, then we move on to the next talk. That is by Professor Nakshi K. Sharma of South Campus, Delhi University. And she was earlier at IIT Delhi, and then she moved on to the university. And most of us know her. And she has been responsible, let me say, for promoting photonics or optics in the university. You can share.
Is my screen there?
Not yet.
Not yet.
ये कहाँ दो रहा हूँ
एक्चुअली इसलिए आया था ना जो कुछ प्रॉब्लम हो जाएगी तो वहाँ पे नहीं होती है जैसे संजय का टक जाना ना
हाँ ओके थोड़ा क्या
शेयर किया है मैडम तक तो आ जाना चाहिए
तो ये इनाक्षी
नहीं आया ना
नहीं अक्षर में ये कहाँ वाइफ तो जाके हेल्प करना तो चाहिए दोनों अलग अलग रूम में बैठ रहे
नाउ
हाँ
आ गया राइट
okay. Good afternoon. My talk is actually not on something which I am now working on, but it is something which was done as a project under the guidance of Professor Kehar Singh 34 years ago by a then MSc student of mine, Mamta Chowdhury. And it was on binary computer generated Fourier transform hologram. So I just thought I'd revisit the project on Professor Kehar Singh's 80th birthday. So it's not an area in which I'm working, so I have to spend some time recollecting how things worked, but I'll try and make a small presentation on it. Before that, I would like to share a quote from Henry Ford which says, anyone who stops learning is old, whether at 20 or 80. Anyone who keeps learning stays young. The greatest thing in life is to keep your mind young. And that is exactly what Professor Kehar Singh is a role model for us. Sir, on your 80th birthday, I wish you a long, healthy and active life ahead. May you continue to spread your wisdom, knowledge and inspire young minds to continuously read and learn more and more, which everybody now is giving up.
Thank you.
Yeah. So as I said, my small talk today is on binary computer generated Fourier transform hologram by a young MSc student in 1987 as an MSc project. And just for Professor Kehar Singh's recollection, I put a picture of hers from then. And she worked under the guidance of Professor Kehar Singh, and this is the top of her thesis. I should mention that as I was clearing my office at retirement, I found a copy of this 34-year-old MSc thesis, and it amazed me that we had done this work that many years ago. So this was a work on computer-generated hologram. And conventionally, as we all know in textbooks also, hologram is recorded by interference of coherent light with the object wave to record both amplitude and phase. But if I can mathematically describe an object and compute the hologram field numerically and somehow transfer this information to a transparency of photographic plate, I would have a computer-generated hologram. The advantage of this came up in the process is that one can create images of objects that actually do not exist in the physical world. So, similarly, a computer-generated Fourier transform hologram is something which has the Fourier transform of the object recorded. So we all remember perhaps that a lens can act as a Fourier transforming element, which means if I have a field distribution in the front focal plane of a normal convex lens, then what you get in the back focal plane is the Fourier transform of the distribution in what I now can call an object plane. So if I can by a computer generate this field, what I have actually generated is a Fourier transform, and that I would call a Fourier transform hologram. And if I now place this Fourier transform hologram in the object plane, what it will generate is the Fourier transform of the Fourier transform, which will be the object itself. So this is the concept of a Fourier transform hologram. So the problem is that the process involves fields which are inevitably complex. So it involves actually creating a complex field and somehow recording this complex field onto a transparency. What we considered for the project was for simple objects for which Fourier transform could be calculated analytically. So Mamta considered a letter T, and finally she also looked at, this is, if you can make out, is MC, which were the initials of her name. And the letter T or the letter MC written in this form could actually be represented by a combination of rectangular apertures. So what she did, for example, was for the letter T, you could write it as a function of a rectangular product of rectangular functions in the X and Y direction. The Fourier transform could be done analytically, so she obtained the Fourier transform. The real part, separated the real part and imaginary part to obtain a point-by-point amplitude and phase of the Fourier transform function. The next question was to somehow code it onto a transparency. To do that, the hologram field was divided into sample points. So a grid of nx by ny samples was created, and at the center of each sample point, the amplitude and phase of the field required in the Fourier transform was known. Just reminding ourselves that the Fourier transform of the Fourier transform will give you the object, and hence the bandwidth of the spatial bandwidth present in the Fourier transform. So that decided the sampling size nx, ny. That each sample point, as I said, had an amplitude and a phase, and in general, we cannot create structures that can directly control both amplitude and phase, and some kind of an encoding process had to be defined. And finally, this encoded field had to be put on a transparency. So the encoding process, which I think I've slightly understood with some difficulty over the last few days, was the one proposed by Lohmann and Brown. And it's based on the fact like this, that if I have a beam which is at a slight angle alpha, illuminating, let us say, an area which is divided into samples along the x direction, then this parallel beam has its the 0 to 2 pi phase change planes marked like this. So when it hits this plane, the so-called holographic plane, if I have a hole created here, it sees a different phase of this as compared to a hole at a different point. So in this little sample, which is actually the size of this spread, the position of the transparent hole created on the screen will tell you the phase of the incident wave which will be present there. This is the kind of concept used by these authors in the detour phase hologram concept. And so for this is what Mamta used. And so the hologram plane, or the Fourier transform calculated plane, was divided into sample cells. She knew the value of the amplitude and phase at each cell. And so to encode amplitude was relatively simple. All that had to be done was a rectangular hole was made which had dimensions proportional to the amplitude, and in consonance with the detour hologram detour phase concept, a rectangular hole was shifted with respect to the center of the sample space. So this is the nth sample, which has dimensions dx and dy on this direction. This was the center. A rectangle is created here. I did not exactly figure out what decided the width of the rectangle, but I understand that it was dependent upon the angle alpha. In fact, it turns out to be about proportional to 1 by alpha. This height is proportional to the amplitude of the signal there, which is normalized to have a maximum value of 1. And the shift from the center was directly proportional to the ratio of pi to 2 pi. And what was done was, the first attempt was to create this hologram by hand, which means on a black chart paper, a grid of 20 by 20 squares was created, and inside that little rectangles were cut by a sharp surgical knife according to the detour phase technique, and the sheet was then photographed to create the hologram transparency. And this is a picture of that 20 by 20 hologram sampled at 20 points. As you see, they are not exactly in the center of each. They're shifted according to the phase requirement. And then the reconstruction was done by illuminating the holographic plate, which was placed in the front focal plane of a lens by a parallel helium neon beam. And this is what the reconstructed image of the letter T. This was a hologram of the letter T, and this was the reconstructed image. From what I recollected, we got a large number of images all over the plane. That is because the moment the Fourier transform for continuous function g of xy would be a single function located at the center of the the Fourier space. But the moment you sample it, it actually becomes a periodic function, and hence probably that's why we actually saw, I don't remember too much, we saw a large number of t's in the plane. Then the next attempt was that once we knew that we had to generate essentially a set of rectangles of specific dimension and specific positions, the whole system could be programmed and printed out on a dot matrix printer. So this is a print which you would have if you had 40 by 40 points. And a picture of this would create a transparency where the black would convert to the transparent part in the negative. And this is now again the reconstruction with a 40 by 40 points hologram created on the dot matrix. This was 66 by 66 points and the dot matrix. And this is a picture of Mamta now. She did her PhD eventually with me and is an associate professor at Hansraj College of Delhi University. Thank you. So this was my just a short presentation, just a revisit to the project done 34 years ago under the mentorship of Professor Kehar Singh. Thank you.
Thank you. Thank you. Are there any comments?
Just a comment.
Yeah, Professor Kehar Singh.
Thank you, Inakshi, for taking me down the memory lane.
Yeah. So it was a great pleasure. It was that.
Thank you very much. Those were the days when we didn't have computers.
Yeah,
these days youngsters can generate this in a matter of fraction of a second.
But sir, I'm convinced that they learned much more then by doing things with their hands than they are learning today by doing everything on a software.
I think so.
Okay, any other comment?
Only good preach of that day of the
Sir, can I speak a word? Mamta Saini here.
But Mamta has joined I just sent her the link, so she has joined.
So I want to take this opportunity.
Share your
Mamta Saini is the student who had done the project. She's just joined in also.
When are you, Mamta, now?
I am teaching at Hansraj College.
Oh, actually, you can unshare now.
Okay, I can unshare, yeah.
That's creating a problem.
I would just like to thank Professor Kehar Singh for having given me this opportunity. It was really a very good experience. Learned so much from him, and I would like to wish him good health.
Thank you.
Thank you, sir. Thank you, sir.
Thank you, Mamta, for joining.
Oh, thank you so much, ma'am, for giving the opportunity. Yeah.
Thank you.
Then we move on to the next talk by Professor Shenoy. Professor Shenoy is a colleague in the department. And
I'm there.
Yeah. Okay, Shenoy.
Are you able to see the screen?
Yes. Yeah. You can make a full screen now. Full presentation. If it works. Yeah, it's working. Okay, good. Nice.
Thank you very much. So, good afternoon, everyone. This is a seminar on information optics and photonics in celebration of 80 years of Professor Kehar Singh. I thank the organizers for planning this event, and then I wish Professor Kehar Singh a very happy birthday and many more happy returns of the day.
Thank you.
My current research interests are three topics these days: all optically pumped semiconductor amplifiers and lasers, light scattering by turbid media. Here there is a PhD student who is working, and there is a PhD student working on this topic. And the other area is electro-optics of liquid crystal waveguides and phase plates. My collaborator is Professor Aloka Sinha. One student has completed his PhD and currently doing postdoc in Israel. And we also have a DRDO-sponsored project in this area. So today I choose to talk on the first topic, that's all optically pumped semiconductor amplifiers and lasers. The outline of my talk is semiconductor optical amplifier and laser, because many of you may not be familiar with this topic. Optical pumping of semiconductor optical amplifiers, conventional schemes of optical pumping and their drawbacks, The proposed scheme of optical pumping, design considerations, choice of materials, waveguide parameters, output characteristics, and finally conclusion of our studies. And at the end, I will answer why optical pumping of semiconductors. Right, so the basic semiconductor laser structure looks like this. You have a substrate on which there is an active layer and then an overlay to form a double heterostructure. If you take a longitudinal cross section,
sound गई है?
Shinoy, unmute.
Would look like this. So you have the substrate. What? Just 1 second.
Now it is okay.
हाँ, तुम्हारी बीच में आवाज चली जाती है, अदरवाइज
साउंड चला जा रहा था.
Go ahead now.
अच्छा.
Go ahead. Now it is okay. फिर गया. आ गया. बीच में जा रहा है.
अरे मैं इंस्टीट्यूट में हूँ, यहाँ तो इतना अच्छा कनेक्शन है.
ये कोई बात नहीं, चलो कंटिन्यू करो. ओके, फाइन.
ठीक है.
लेट्स सी.
All right. So if you take a longitudinal section, then it would look like this. So we have the substrate, the overlay, and the active layer, and the metal, the yellow colored layer is the metal electrodes to pass a current. So the double heterostructure laser, more details are shown here. So you have a low band gap material in the depth direction. You can see that this material is a low band gap material sandwiched between two higher band gap materials. And if you see the energy band diagram, you will see it like this. And on the right side, what you see is the refractive index. The low band gap material has a higher refractive index, and the cladding layers have a lower refractive index. Therefore, it acts as an optical waveguide and supports a guided mode. And the materials generally, for example, I have taken gallium arsenide, aluminum gallium arsenide, typical band gap energies, refractive index. And if you calculate the V number with a dimension of about 0.1 micrometer here, it comes out to be very small, and it supports a single transverse mode waveguide. Now, why we use the heterostructure is to obtain carrier confinement. So this is the low band gap material. And when you forward bias, carriers are injected into this region. There's plenty of electrons here and plenty of holes here. The point is the forward biasing or passing a current through the diode is to obtain carriers, plenty of electrons and holes in the same region. Now, similarly, if you take a semiconductor optical amplifier, it's exactly like a semiconductor laser, except that the two cleaved ends here are anti-reflection coated, and you have the same structure. So there is a current passing through this, and there is a power input.
इधर रखा था तुम्हारे अकॉर्डिंग में मिस हुआ है यही ना, मतलब यहाँ रख दिया है कॉमन में.
Into the semiconductor amplifier region. So this is a fiber pigtailing. What is shown is schematic showing input and output coupling of an SOA through fiber pigtail and micro lens. So if you see the structure, the actual structure of a semiconductor optical amplifier, which is there in our lab, and all the measurements that we have done with this chameleon, it's a 14-pin butterfly package, and it's electrically pumped by injection current across the PN junction, as you can see here. And the optical gain is due to current injection, because current injection leads to the electron hole pair generation, and a typical gain spectrum is shown here. Gain versus wavelength, what is plotted, typically a bandwidth of about 100 nanometer. Now, optically pumped SOA. What is this optically pumped SOA? Here, the carrier pairs are generated by an optical beam. It's just like pumping a typical erbium doped fiber, for example. So the gain here is due to optical injection. That is, optical injection leads to carrier, because by absorption of the photons, there is a electron hole pair which is created. So you have plenty of light which is coupled into this, then there are plenty of carriers created. And then the signal can get amplified as before by stimulated emission. So carriers are generated by absorption of input pump. And this has an optical to optical control, no PN junction required, and so on. We will see this in the coming slides. So just as an analogy to make it familiar, we are very familiar with the erbium doped fiber amplifier, where you have a 990 nanometer laser which pumps, and we have amplification around 15. Note that these layers actually comprise of a number of layers here, actually energy levels. There are number of levels which make this bunch of levels at 4i, 13 by 2 and 15 by 2. If you see analogously here, the energy bands in a semiconductor, which comprises of large number of allowed energy states in the conduction band and valence band, we could also pump just like this. For example, if you use a 1480 nanometer pump for EDFA, then you are using the same two bands. It's a quasi two band amplifier. So you excite atoms from here to the upper level, and then you build a population inversion and obtain amplification by stimulated emission around 1550. Exactly like this, it is possible to pump the semiconductor by another laser and create large number of electron hole pairs and lead to amplification by stimulated emission. So that's the idea of optical pumping. Instead of passing current and creating electron hole pairs here, we have light which is generating electron hole pairs. Light pump light at a different radiation. That's the idea of optical pumping. So then rest is very simple. It's just like the erbium doped fiber amplifier, where you have a pump laser and signal laser combined with the WDM coupler, and then you have erbium doped fiber, and then you have amplified output which comes out. So these details are very well known and listed and discussed in various books. The conventional scheme of optical pumping, where you used a WDM coupler and put the pump and the signal along the same line, does not work, however, for semiconductor lasers, because the absorption coefficient of semiconductor is of the order of 10 to the power of 4 centimeter inverse, whereas it is 1 to 2 centimeter inverse in erbium doped fibers. And the length here is just about 500 micrometer, where in erbium doped fiber amplifiers we use 10 meters of the fiber. And therefore what happens is, if you launch pump in the same direction, only the initial portion absorbs the pump light, and then rest of the region remains unpumped. But with the typical 100 and 200 milliwatts of power. If you put more power, of course, it will damage the semiconductor. So that is the limitation. And there are other schemes which people have tried, that is by illuminating from the sides. But the problem is, only a small fraction of pump power is used to excite this region, and hence it is very inefficient. So what we have proposed is, so let me skip this. What we have proposed is an optical pumping scheme by using coupled waveguides. So proposed scheme of optical pumping through coupled waveguides. The advantage is that by adjusting the coupling, so this is the actual view and this is the top view. You are looking from the top here. Then you can see the active waveguide and pump waveguide, and coupling by evanescent coupling between the two waveguides. The typical dimensions I will show later. Then these are very small dimensions, typically 0.2 micrometer, 0.3 micrometer, and the separation S of Z is also variable. And this is what is meant by guided wave coupling, coupled waveguide coupling of pump into the signal. The advantage is you can excite all over the length of the active waveguide. If you couple from one end, the pump will die down initially here. Here you can control the coupling and excite all the entire waveguide, just as the metal electrode which passes injection current through the entire active region, you can achieve the same thing. And then, so this is the typical structure which we have analyzed in great detail, the choice of materials, the waveguide parameters. So these are all a matter of details. I will not go into this. And then co-propagating, contra-propagating, all the calculations and simulations we have done. And I'm showing just this characteristic for those of you who are familiar. For you, you know that there is a minimum pump power required to achieve transparency in the semiconductor and then onwards gain. And you can see that. And depending on the signal power, the gain is different. The input signal power minus 40 dBm, minus 30 dBm, minus 20 dBm. The gain characteristics are shown here as a function of pump power. So typical powers required are about 200 to 300 milliwatt. And what is shown here is the wavelength dependence of gain. This is also typical curves. And depending on the pump power, you get a wider bandwidth and so on. Now, this is the saturation characteristics. All of these, the point is, all of these characteristics look exactly similar to the conventional electrically pumped semiconductor optical amplifiers. And the numbers almost are similar. Now, some experiments we have done to check this. I will not go into this detail, but here is again, we can see this is done in our lab using the SOA picture which I had shown you earlier. So this is pump power versus gain. The gain is relatively small. That's because we don't have much pump power in our lab. We did not have the, at the 1310, we did not have a higher pump power, but one can get a higher gain if you use higher pump power. Now, I come to the conclusion of our studies. That is, optical pumping through waveguide coupling is efficient over conventional optical pumping schemes. Conventional means either pumping from the end or pumping from the sides. There are a lot of people working on this, and there is a white paper from Corning on optical pumping of semiconductor lasers. In fact, Professor Paul first saw that and he sent it to me. And the second point is coupled ridge waveguide structure is a suitable choice from the fabrication and the design perspective. And an appropriate choice of materials and waveguide parameters gives an optimum design for all optically pumped semiconductor optical amplifiers. Now I come to the question, why optical pumping? In fact, we have filed one patent application, and also we have communicated a paper on this. And
time is...
Yeah, so this is my last slide. Yeah, this is my last.
Okay.
That's why yeah. So enables optically controlled signal gain. It's all optical. When you have all optical process, you can control the signal gain by optical power, not electric. Better control over longitudinal carrier profile. I cannot discuss this in detail here, but as you saw, pumping is done all along the length, and we have a control which region of the active layer has to be pumped more or less. For remote pumping in electrically hazardous environment, because remember there is no electrical connection at all, simply optical pump is used, and it is no PN junction and no electrical contacts, and it is no more a laser diode. It is simply a semiconductor double heterostructure. It is not a PN junction. Thank you.
Okay, thank you, Shanoy. Any questions, comments? Okay. If there are no questions, comments, then as they say, they'll tham ke baitho, ab meri bari hai. So I have to speak and I will share. Jovi, you have to keep time, all right?
Yes, sir.
Okay. Can you see the slides?
Yes, sir. Yes, yes.
Okay, so first of all, I would like to wish Professor Kehar Singh many, many years to come. Happy birthday, and it is my, selfish desire that I continue to have your blessings for many more years to come. We want to see the results of optics at 80 and optics at 90 and so on. So many happy returns of the day, sir. So what I'm going to talk about is holography. Of course, talking about holography in front of Professor Kehar Singh and his plethora of students is like ulte baans bareli ko, but still I will do that because this is how I started my learning in optics some 50 years back, 49 years back. So in July 1972, I, all of 17 years old, entered the portals of this great institute. And at that time, I did not know how great the institute was, but actually eventually when I learned through this, the portals of this institute, the different degrees I obtained, and then I learned. And this is what I was at that time, if you can recognize. And this was Professor Kehar Singh around the same time. This is 1973, 1974. A part of our MSc course, which was being taught by Professor M.S. Soda, was on atomic and molecular spectroscopy. And then at the end of the course, he said, now Professor Kehar Singh will teach about Fabry-Perot interferometer and other interferometers. And this is how we got introduced to Professor Kehar Singh at that time. If you recall, 1971 was the time when the Nobel Prize was given to Denis Gabor for holography, and it was very fresh. And I'm sure during that teaching, of course, Professor Kehar Singh must have talked about holography, and that got my attention and interest. And eventually I did my MSc project with Professor Kehar Singh on holography, and that is why I'm talking about holography today. Later on, of course, I joined the department, and you can see the picture that at the top, Professor Kehar Singh and myself about 10 years later. This is 1987, if I remember correctly. In between, some of you will recognize Professor H.C. Gupta. And the lower photograph is I'm welcoming Professor Kehar Singh to Photonics 2018. So this is very recent. But of course, over the years, we have all grown older, but Professor Kehar Singh has become younger. You can see the young dashing man giving lecture in February 2020. Okay, so that is how we have all noticed how young he has become over the years. So coming to holography, why it is attractive to a layman? Holography is fascinating subject as it promises to create a 3D image of an object. Whereas to a scientist, holography is fascinating subject as it provides a way to record and retrieve phase information of a wave which is otherwise difficult. In 1973, there were not too many books when I joined.
Your screen is not visible. Your screen is not visible.
Not visible?
Yes, it's visible.
Yes, it is visible for us, sir. There is no problem.
Oh.
It is visible, sir.
It is perfectly fine. Yes.
Oh, sorry.
Okay.
Sorry.
Yeah.
Sorry.
Okay, fine. So in 1973 or 70, when I joined for the project, there were not too many books. I learned a lot from a book which was by H.A. Caulfield and Liu, Applications of Holography. And the example that I learned of this, which was most striking example that they had given to introduce holography, I still use as an example to introduce the concept of holography that I learned from that book in my classes. So what is the example? Suppose we have positive and negative numbers, let us say between 100, minus 100 and 100, and we have a storage device which can store only positive numbers. How do we store these numbers? And this is the core question I have posed to my class year after year. And after many suggestions, eventually one of the students will come up with the right answer, that we add a large enough number, say 150, to all the numbers. They all become positive, store them, and on retrieval, we subtract this reference number 150, and that is how you can store positive and negative numbers. And negative here is nothing but a phase change from positive to negative. And thus we use a reference code to code a signal in a desired format, then reverse the process. And this is how holography works. Then I move on to describe how do we observe things. So then I show this photograph, which is, of course, most of the students do recognize, whether in school or college or in the class, is that of Einstein. And then I show also this picture, which is again of Einstein. One is young, the other old. This picture, the eyes of Einstein are looking at you. And what I tell the students, no matter where you are standing in front of this picture, whether on the extreme left or extreme right, the eyes will always follow you, as if eyes are looking at you. Whereas in this picture, eyes will not looking at you, no matter where you stand, it will not look at you. But this will not happen when the person himself is there in place of the picture, because then you see the directionality. And this is a manifestation of the fact that while making a photograph, you actually lose the phase information and the directional information. So in the first picture, the person is looking into the camera, and so the eyes are also focused in that. In this, person is not looking into the camera, and so eyes will never be focused on the person who is watching the picture later on. So this is how the phase information is lost. I mean, this is just manifestation of a photograph where the holography is different, and we'll come to that. Then we discuss how what is the meaning of seeing or observing something. So let's consider a star which is thousands of light years away, and it is sending light to the Earth where we are observing, and different successive wavefronts are reaching our eyes. And it is these wavefronts which are making us see this star. So in these thousands years, if the star has vanished and these wavefronts are still coming to us, we will still see as if the star is there. So there's a time lag between the two. What actually we are seeing is what is the wavefront is showing us. And this wavefront, if you move across, will show different perspectives. But if you record this wavefront or make a picture of this, then this will not happen. All right. So photograph is also a record for posterity, and this is also what I'm trying to say is that when the star is not there, you can still see. If the wavefronts which left the star several years back, thousands of years back, are still reaching us. Now, if we have a mechanism of storing this wavefront, not the picture, storing this wavefront, then actually we can release that wavefront anytime that we want, and we will see the star. And this is the essence of holography. Now the question comes, how do we store the whole wavefront? And that is what we did in that particular number example. We have to have a reference wave. We have to record the whole wave, amplitude phase, and we have to use the technique of interference, where we add an additional wave, just as we did in the case of those positive and negative numbers, and then use the same wave to retrieve it back. And this is the typical picture. This I got from Joby several years back, and this is a typical how the holography works from a point source. And of course, all objects are made of points, so this theory is valid for all objects fully. And in the region of overlap of the two waves, the reference wave and the object wave, you record something, then it becomes an interferogram, and then this becomes kind of a grating, complicated grating, and when you illuminate this with a reference wave, this grating gives you +1 and -1 orders, and that gives you a virtual and real image. So actually, the holography is also a beautiful example where the one process recording is interference, and the reconstruction is actually diffraction. Although we of course know that both these phenomena are one and the same, but here they very clearly they delineate themselves. Okay, so what is the meaning of 3D? So the image created by the hologram is a replica of the object in 3 dimensions. This is how we understand. But it is only a limited view, as if we are looking through a window represented by the hologram. So if you have a hologram of let's say 1 inch by 1 inch, then you are only that much window view is available to you. So the different perspectives that can be seen are limited by the size of the window. In this respect, it is actually not a 3D reconstruction of the object. Actually, it is a 3D reconstruction of the wavefront in that limited size. But it is not a 3D, and that is sometimes the students get excited about 3D, but this is a very limited view of the 3D here. If a hologram is broken into smaller pieces, you all know that each piece will construct the entire image of the the image of the entire object. However, due to the smaller size, not only the resolution in the image will be reduced, but the window size is also reduced, and hence the perspectives available will now be very small, will be much more limited. So these are the two things that happen. So that is how one should use this 3D business of 3D holography 3D reconstruction with a pinch of salt, with little careful. Now, of course, these days, these lot of laser projections which are happening on the stage and otherwise are called holographic. But of course, those are not holographic. That's a misuse of the term, I would say, in some sense. But the holographic term is being used in the string theory these days. So I just want to spend 2 minutes on that. One can view a hologram as a two-dimensional encoding of information from a 3D region. This is how it is happening. You have a 3D object and the entire wave that is coming. You record the entire information that is in the wave on a 2D record, and then you can get that information again from the 2D into a 3D region. So this is a way of one dimension reduction in the storage of information. Researchers in theoretical physics use this term to say holographic principle to this effect, to reduction from 3 dimension to 2 dimension or 4 dimension to 3 dimension. It has been established that when an object falls into a black hole, its information is available on the surface of the event horizon. Event horizon is the place where the light can, if it enters beyond that, then it will not come back. So that is the event horizon. Thus, the 3D information inside a black hole actually can, in principle, be obtained from the information on the 2D surface of the event horizon. I mean, you can add this to make it a, if you add time, it becomes 4D information to 3D information, 3D surface. But let's forget about time at the moment. This is what is called the holographic principle. When a few years back, when I heard the holographic principle from a theoretical physics, and I was very confused what they are meaning. Now I understand a little bit of that. So it has now been put forth, and this is a conjecture which is being studied, that since black hole can come up in any area of universe, this holographic principle must be applicable to all over the space. And then that what people are saying now, thus it is sometimes said that the universe is nothing but a hologram of something. But that's a too much oversimplification. Somebody from Stanford had said that the world doesn't appear to us like a hologram, but in terms of the information needed to describe it, it is actually one. So it is a hologram in terms of the information, but it's not really a hologram, as some people get excited and say. Finally, I just want to quote from the editor of the Scientific American, which says that the amazing thing is that the holographic principle works for all areas in all space-times. We have this amazing pattern there, which is far more general than the black hole picture that we started with. And we have no idea why this works. What this is telling us is that there is a description of the world we should be looking for, which will be much more economical in terms of information than the one we have right now. And this will presumably have to do something with quantum gravity. And this is where it is. So holographic word has moved into another domain, and people are studying this particular principle. It's a very hot topic in the theoretical physics area. So that's it. That's what I wanted to just spend some time on the word hologram and holographic and how I teach this. And thank you very much. This is a photograph from Photonics 2018 when we had honored Professor Kehar Singh and Joby Joseph. You can see it. Thank you very much.
Thank you, sir. So we can take one question in case there is any.
Any comments?
Yeah, I think if not. Thank you, sir, and thank you very much.
Kehar Singh probably wants to say something.
Oh yes, Ragesh.
Wonderful presentation.
Sir, about comment on the holography and string theory, there is also a similar comment using the holographic interpretation of hologram using the Wigner distribution. Exactly similar kind of idea also exists.
Okay.
Okay, thank you, Ragesh. So thank you, sir, and thanking everybody for all the speakers in the morning session. And we are maybe half an hour late. Of course, I think we will start at 2:30 itself. Otherwise, we will not be able to finish. So you don't have enough time for lunch, but please have it.
You think 2:30 is enough?
Yeah.
Professor Singh?
Maybe 2:45 कर लो. In between 15 मिनट कर दो यार. अभी
I'm a frugal eater, so for me it's okay.
No, everybody is at home only most of the time. I mean, some people are.
2:45 is fine.
So maybe 2:45 is okay, Jovi.
Yeah, 2:45. So Ajit Kumar sir, we will start.
Ajit Kumar will start at 2:45.
2:45.
Ajit muted हो.
Okay, sir.
Okay.
Ajit unmute करो पहले अपने.
Yeah, that is fine for me. Okay. That is fine for me.
So for all others also, I mean, we'll start the session at 2:45 and then continue follow the rest of the. Thank you very much.
It will remain the same.
Yes, same link and same link. It will not be closed also.
Yeah. Link is open. You can leave and you can come back.
Okay.
Thank you. See you at 2:45. All of you. Thank you.
Okay, fine. All right.
End string. Your string will stop immediately.
Jogi, maybe you can stop recording and then record again because otherwise it becomes a too big a file.